Hello again, and welcome to Just About Earth, where big questions unfold slowly and science tucks in beside curiosity like an old friend. Wherever you are, and whatever time it happens to be in your corner of the world, I'm glad you're here. If you're listening right now with heavy eyelids or a full mind, you're not alone. Maybe you're stretched out under a blanket, maybe curled up on the couch, maybe the sun's gone down, or maybe it's just peeking over the edge of morning. And wherever you find yourself, you're sharing something with every other person listening, every other creature under the same sky. You're living on a planet that's just barely balancing the conditions that make life possible. It's easy to forget how rare that is. Earth feels stable, predictable. There's the comfort of routines, seasons that change more or less on time, rain that usually falls when it's supposed to, a moon that waxes and wanes with calm, silent persistence. We build homes, plan holidays, raise families, argue over parking spaces, all with the quiet assumption that this planet will keep being home. But sometimes, usually late at night when things get quiet, a question drifts in. Could that ever change? Will Earth ever become uninhabitable? It's a question that arrives not like a knock at the door, but more like a shadow at the edge of thought. It isn't a doomsday scenario, not quite. Not fire and brimstone or giant explosions, it's subtler than that. What happens if things shift just a little too far? If the systems that keep us fed, cooled, warmed and breathing begin to unravel? Could we, with all our clever tools and machines and stories, ever find ourselves looking back at a planet we once called home? From somewhere else? Before we try to answer that, let's sit with it for a moment. Not to worry or spiral, just to acknowledge the scale of what we're really asking. We're not talking about whether a city becomes unlivable for a decade, or whether a storm knocks out power for a few days. We're asking about habitability at its deepest level, a world where basic human needs, breathable air, drinkable water, survivable temperatures, can no longer be counted on. And it's worth noting, right from the start, that Earth hasn't always been cosy for creatures like us. In fact, for most of its 4.5 billion year history, it's been anything but. Life has existed here in some form for about 3.8 billion years, but for most of that time it was microbial, primitive, clinging to vents in the sea or floating in nutrient soup. The kind of life that doesn't care whether there's oxygen in the air or sunlight in the sky. Humans, on the other hand, are picky. We need a very specific set of conditions: temperature ranges, atmospheric pressure, stable seasons, fertile land, a protective ozone layer, and access to fresh water. And all of that has only been reliably in place for a brief slice of geological time. Still, even in that brief time, things haven't been exactly calm. The planet has gone through ice ages and hothouse periods. Oceans have risen and fallen. Entire species have disappeared. Not just a few birds or frogs, but entire ecosystems, wiped out by changes they couldn't adapt to fast enough. What's unusual about the present moment is not that the climate is changing. It's that it's changing rapidly, and in many cases because of us. That part, the human part, will come up often as we continue. Because asking whether Earth will become uninhabitable is, in some ways, another way of asking whether we'll push it too far. Whether the things we build and burn and bury and extract are nudging the systems of the planet out of balance. Whether the very intelligence that allowed us to understand biology and build cities might also be the thing that tests the limits of Earth's resilience. But we're getting a bit ahead of ourselves. For now, let's take a step back and look at what makes Earth habitable in the first place. What are the factors, the physical and biological ingredients, that make this particular rock in space capable of supporting us? Start with the basics. Earth sits in what's often called the Goldilocks zone. Not too hot, not too cold, just the right distance from the sun to keep water in a liquid state most of the time. That might sound simple, but it's not a given. Move Earth a few million kilometers closer to the sun, and temperatures would rise just enough to disrupt water cycles and potentially boil away oceans over time. Move it farther out, and the atmosphere might not retain enough heat to prevent global freezing. So right away you can see how narrow the window is. We are, quite literally, in a lucky orbit. Then there's the atmosphere. Not just the presence of one, but the precise mix of gases. Roughly 78% nitrogen, 21% oxygen, with a sliver of carbon dioxide and other trace gases. That mix didn't appear overnight. Early Earth had a toxic atmosphere, rich in methane and ammonia. It took billions of years, and the emergence of photosynthetic life, to shift that balance toward oxygen, which is what allows us to breathe today, and even now it's a delicate balance. A few percentage points too far in either direction, and human life would be impossible. Pressure matters too. The atmosphere provides not just breathable air, but the pressure needed to keep water from evaporating or freezing at Earth's surface. Without it, our blood would literally boil in our veins, even at room temperature. Gravity helps with that. It holds the atmosphere in place. So when people wonder if we could just move to another planet if Earth becomes inhospitable, that's part of the challenge. Most planets don't have the right gravity to maintain an atmosphere like ours, or they have the wrong mix of gases, or they orbit stars that flare too often, or they lack a magnetic field to shield from radiation. Ah yes, the magnetic field. Another quiet protector. Earth's liquid iron core generates a magnetic shield that deflects solar winds and cosmic rays. Without it, our atmosphere would slowly be stripped away. Like what happened on Mars. Radiation would increase. DNA would break down more easily. Life would become much harder, especially on the surface. And that magnetic field isn't guaranteed to last forever. It's weakened before, shifted poles, even temporarily collapsed. Each time it has recovered, but each time it's taken thousands of years. Then there's water, the lifeblood of life as we know it. Earth has it in abundance and in all three states: solid, liquid, gas. That variety allows for weather, seasons, glaciers, rainfall and life cycles. But it's also subject to imbalance. Melt too much ice and sea levels rise. Evaporate too much moisture and deserts expand. Freshwater sources are finite. Aquifers can run dry. Rivers can be diverted, polluted or overused. A planet with the same amount of water but in all the wrong places is just as deadly as one with none at all. And finally, there's biodiversity, the network of living things that stabilizes everything else. Trees absorb carbon dioxide and release oxygen. Bacteria fix nitrogen in soil. Insects pollinate crops. Coral reefs buffer coastlines. When these systems are healthy, they act as a kind of biological insurance policy, absorbing shocks, self-regulating, adapting to change. But they're also vulnerable. Disrupt one piece and others begin to falter. Lose enough species and the system doesn't recover. So when we ask whether Earth might someday become uninhabitable, we're really asking how many of these systems would have to fail, and how likely that is. It's not necessarily a single event, it's more often a gradual tipping, a series of changes that accumulate until certain places, then entire regions, can no longer support human life. A city becomes too hot to survive without artificial cooling. A river runs dry after years of drought. A coast disappears beneath rising water. A storm wipes out infrastructure faster than it can be rebuilt. Over time, habitability isn't lost all at once. It becomes patchy, uneven. Some regions remain livable for a while. Others become marginal. Migration increases. Resources become strained. And yet, the planet itself will still be here. That's the tricky part. Earth isn't threatened with disappearance. It's not going anywhere. What's at risk is its ability to support life as we know it. And not just any life. Our lives, our societies, our agriculture, our assumptions about weather, water, and shelter. Some scientists refer to this idea as the planetary boundaries framework, a set of 9 critical thresholds that, if crossed, could push the Earth system into a new and potentially unstable state. These include things like climate change, biodiversity loss, ocean acidification, and land system change. As of now, we've already crossed several of them, or are very close. That doesn't mean immediate collapse, but it does mean increased instability. Still, instability is not inevitability. Systems can recover. Some tipping points are reversible, others are not. The question isn't just whether Earth can remain habitable, it's whether we're willing, and able, to keep it that way. But before we explore what that actually looks like, the kinds of shifts happening in our atmosphere, our oceans, our soils and skies, let's linger just a bit longer in the idea of what makes this place feel so perfectly tuned for us. Because when you understand the balance, the margins, the sheer narrowness of the zone we live in, the rest of the journey makes more sense. The Earth, for all its beauty and resilience, is not an unshakable fortress. It's more like a well-tuned instrument. Strong, but sensitive. Capable of carrying the weight of life across millennia, but not immune to wear. And if we know that, really know it, then maybe we begin to see the question not just as a warning, but as an invitation. What happens next is not entirely out of our hands. So, as we shift from possibility to probability, from the conditions that support life to the changes that threaten it, let's keep our eyes open and our minds calm. There's more to see, and the path ahead, while uncertain, is still very much ours to walk. If you've ever watched a sunrise turn the edges of a landscape gold, or stood outside on a mild evening as a soft breeze wandered through the trees, you felt it, that quiet sense of rightness. The feeling that this place, for all its noise and complexity, was somehow made for us, or we for it. It's easy to forget that it didn't have to be this way. There are countless other arrangements of temperature, light, atmosphere and gravity that would have made Earth entirely unwelcoming. The version we live on is just one outcome, a fortunate one. It starts with the Sun. Our star isn't particularly large or rare. In fact, it's fairly average. A G-type main sequence star if you're keeping track, but its steadiness and the Earth's position relative to it create conditions that are remarkably stable. We're about 93 million miles away, which sounds like a lot until you consider that even slight variations would be enough to push us out of the habitable zone. Not too hot, not too cold. This distance lets water remain mostly liquid at the surface, which is critical. But the orbit matters too. Earth's path around the Sun is close to circular, with only a mild eccentricity. That means we don't swing wildly between searing heat and deep freeze as the year goes by. Then there's the tilt. Earth leans on its axis by about 23.5 degrees, which gives us seasons. If it were perfectly upright, large parts of the planet would experience far less variation, and some might never get the full light they need to grow crops or warm up after winter. If it tilted too much, the seasons would become extreme and potentially destructive. The current angle is one of those small invisible features that turns out to matter a great deal. It distributes sunlight across the globe in a way that allows for forests in some places, deserts in others, and rotating rhythms of planting and harvest. Another quiet contributor is the Moon. You may not think of it as a climate feature, but without it, life on Earth might have evolved very differently, or not at all. The Moon helps stabilize Earth's axial tilt. It's like a counterbalance, keeping our rotation from wobbling too much over long periods. Without it, Earth's tilt might swing more wildly, shifting climates in ways that could make it hard for ecosystems to settle. The Moon also affects tides, which play a crucial role in coastal ecosystems, and may have even been essential to the emergence of life in the first place, offering tidal pools where early molecules could mix, concentrate, and interact. Then we come to the air itself, the atmosphere. A blend of nitrogen, oxygen, argon, carbon dioxide and other trace gases, layered like an invisible shell around the planet. It filters sunlight, traps warmth, and burns up small asteroids before they can hit the ground. Oxygen, of course, is the part we tend to focus on because we need it to survive. But even that took billions of years to build up. The Great Oxygenation Event around 2.4 billion years ago was one of the most dramatic shifts in Earth's history. Before that, the planet was largely unbreathable for modern animals. The oxygen came from tiny organisms, cyanobacteria, that slowly transformed the atmosphere through photosynthesis. Without them, the air we breathe wouldn't exist, and with too much oxygen, the risk of spontaneous fire increases dramatically, so even there the margin is narrow. Carbon dioxide, despite its reputation, is also a key part of the balance. It traps heat in the atmosphere, keeping Earth warm enough for liquid water. Without it, the average surface temperature would be well below freezing. With too much, the planet overheats. Think of Venus, which has an atmosphere thick with carbon dioxide and surface temperatures hot enough to melt lead. Earth's carbon levels have fluctuated over time, sometimes naturally, sometimes not. But the narrow band of concentrations we've experienced during human history has made agriculture, settlement, and society possible. Water, of course, is everywhere on Earth, in oceans, lakes, rivers, glaciers, clouds, and even underground reservoirs. It covers about 71% of the surface. But more important than how much we have is what state it's in. Earth is the only known planet where water exists abundantly as a solid, liquid, and gas all at once. This is partly due to our distance from the sun and partly due to atmospheric pressure. It's what drives the water cycle: evaporation, condensation, precipitation. This constant movement of water shapes weather, nourishes land, and supports life. A world without moving water would be stagnant and barren, but water isn't evenly distributed. Some regions get far more rainfall than others. Some rely on melting snowpacks or seasonal monsoons. In many places, human infrastructure has stepped in to store, divert, and ration water in ways that support dense populations. But those systems are also vulnerable to change. A prolonged drought, a failing dam, a disrupted river system, any of these can tip the balance from livable to precarious. Beneath all of this is the land, not just its surface, but its chemistry. Earth's crust is rich in minerals and elements that support life. Iron, phosphorus, potassium, magnesium, they cycle through soil, water, and plants. Fertile soil isn't just dirt. It's a dynamic, living system filled with microbes, fungi, decaying matter, and fine balances of moisture and aeration. But it can degrade. Too much farming, poor land management, deforestation, these wear soil down until it no longer supports crops. Restoration is possible, but it takes time, and in the meantime people move. Then there's plate tectonics. The slow movement of Earth's crust not only reshapes continents over millions of years, it also recycles carbon and regulates temperature. When tectonic plates subduct, they pull carbon-rich materials down into the mantle. Volcanic eruptions release gases that can, over long time scales, balance atmospheric composition. This geologic metabolism keeps Earth's climate from spiralling too far in either direction, or at least it has so far. Other planets, like Mars, lack plate tectonics, and without that internal regulation, their atmospheres have either vanished or frozen. Even Earth's rotation matters. A full spin every 24 hours keeps day and night cycling in a predictable way. That rhythm governs sleep, feeding, migration, and countless other behaviours in plants and animals. If Earth rotated much more slowly, one side would bake in constant sunlight, while the other froze in eternal darkness. A faster spin would cause extreme winds and storms. So again, the speed we have, ordinary and unnoticed, turns out to be one of those hidden blessings. You can see then how many variables have to line up just right to make Earth habitable for humans. And not just habitable, livable, enjoyable, full of colour and variation. Each system supports the next. Air supports life. Life supports soil. Soil supports water. Water shapes weather. Weather cycles nutrients. It's not a machine exactly, more like a network, one that has adapted and rebalanced over eons, sometimes gently, sometimes violently. We weren't always part of it, Humans have only been around for a blink of time, about 300,000 years, give or take. Our civilization, with cities and writing and recorded history, covers only about 5,000 of those. The Earth has seen 5 mass extinctions, dozens of ice ages, asteroid impacts, supervolcanoes, and long stretches where no creature like us would have stood a chance. Yet we arrived during a period of unusual calm. The Holocene, a geological epoch beginning around 11,700 years ago, brought relatively stable temperatures, rainfall and sea levels. And in that window, we invented agriculture, built civilizations, developed culture and science, and eventually satellites that could look back down on the planet that raised us. That stability is what makes Earth feel like home. We wake up expecting certain things: breathable air, drinkable water, tolerable temperatures. We expect winter to follow fall, spring to follow winter, the sun to rise and set in a reliable arc. We plan months in advance. We build permanent structures. We invest in the future because we trust that the basic rules of the environment will hold. And when they don't, when wildfires appear in new places, when floods come too often, when crops fail, we're reminded, sometimes painfully, of just how much we depend on systems we don't control. It's tempting to think of Earth's habitability as a permanent feature, but it's really more of an agreement, a fragile, ongoing compromise between biology, chemistry and physics. And right now, that agreement is under strain. We'll explore those strains soon, what climate models are telling us, how oceans and ice are changing, and what happens when ecosystems begin to tip. But for now, maybe it's enough just to notice the ordinary miracles that surround us. A blue sky that filters harmful rays but lets light through. An atmosphere that holds warmth without trapping it completely. Rain that falls where it's needed, at least sometimes. A planet that spins just fast enough to stir the air in the oceans without shaking us loose. If Earth feels like home, it's because for a long stretch of time it has been. And the more we understand the pieces that make it so, the better we can see what's at stake, and what might still be possible. If you took a breath just now, slow, easy, without thinking about it, you're already participating in one of the most ancient exchanges on Earth. Every inhale draws in the remnants of countless leaves, ocean swirls and microscopic algae. Every exhale feeds the cycle in return. It's so effortless that we rarely consider the mechanics of it. But the atmosphere isn't just air. It's an intricate living system, shaped by the planet, the biosphere, and even by us. Earth's atmosphere stretches about 10,000 kilometers above the surface, though most of what we interact with is packed into just the bottom few layers. The troposphere, which holds the weather and the breathable air, only extends about 12 kilometers high, the distance a commercial jet might cruise. Above that are layers we don't often notice: the stratosphere with its ozone shield, the mesosphere where meteors burn, and the thermosphere that brushes space. But nearly everything we call climate, everything that shapes habitability for us, happens in that low, dense pocket just above the ground. The composition of this atmosphere is what makes it work. Roughly 78% nitrogen and 21% oxygen, with the remainder made up of argon, carbon dioxide and trace gases. That oxygen, vital for life as we know it, didn't used to be there. For the first couple of billion years, Earth's atmosphere was mostly carbon dioxide, methane and ammonia, a harsh, toxic soup. The shift came slowly thanks to cyanobacteria in the oceans, tiny organisms that learned to turn sunlight into sugar, and in the process began releasing oxygen. Over time, that oxygen built up in the oceans and then leaked into the sky. What followed was known as the Great Oxidation Event, a turning point that allowed more complex life to emerge, eventually leading to fish, trees, mammals, and humans. That oxygen doesn't stay constant on its own. It's maintained through a steady cycle between plants and animals, land and sea. We breathe in oxygen and exhale carbon dioxide. Plants do the reverse, taking in carbon dioxide and releasing oxygen during photosynthesis. It's a partnership that works remarkably well, so long as both sides remain in balance. But when that balance tips, when forests are cleared, or when fossil fuels inject too much carbon into the system, the air starts to change. Carbon dioxide, while only a small fraction of the atmosphere, plays an outsized role in climate. It traps heat, creating the greenhouse effect that keeps Earth warm enough to support life. Without it, the planet would freeze. But with too much, the blanket becomes too thick. Heat builds up, oceans warm, ice melts, weather patterns shift, and the cycles that once kept everything in balance begin to strain. For much of human history, carbon dioxide levels stayed relatively stable. Ice core records show that during the last 800,000 years, a period that includes many ice ages and warmer periods, CO2 levels never rose above about 300 parts per million. Since the Industrial Revolution, however, that number has surged past 420 and continues to climb. The rise isn't gradual or natural. It aligns closely with our use of coal, oil and gas, fossil fuels that release carbon stored underground for millions of years. This isn't just about temperature, it's about feedback. As the atmosphere warms, it holds more moisture, which intensifies storms. Warmer air changes wind patterns and disrupts jet streams. Polar ice melts, reducing the reflective surfaces that bounce sunlight back into space. Darker oceans absorb more heat, which speeds the melting even further. Permafrost thaws, releasing methane, another potent greenhouse gas. One change leads to another, and then another, creating a loop that becomes harder to stop the longer it goes on. But while the rising levels of carbon dioxide are one of the most urgent signals, they're not the only ones. Methane, for example, is more than 25 times as effective as CO2 at trapping heat over a 100-year span. It comes from livestock, landfills, rice paddies, and fossil fuel extraction. Nitrous oxide, another greenhouse gas, is released through agriculture and industrial processes. It's less abundant, but longer lasting. These gases aren't inherently unnatural, they're part of the Earth's systems, but the scale and speed at which we're adding them is what causes the problem. Meanwhile, the forest that once acted as natural carbon sinks or under pressure. Trees absorb CO2 as they grow, storing it in wood and soil, but deforestation, especially in tropical regions, is reducing that capacity. When forests are burned or cleared, not only do we lose their future carbon capture potential, but the carbon already stored is released back into the air. The same goes for peatlands and wetlands, ecosystems that quietly lock away carbon until they're disturbed. The oceans absorb a vast amount of carbon too, more than a quarter of the CO2 released by human activity. But they're reaching their limits. As oceans take in more carbon, they become more acidic. This affects coral reefs, shell-forming organisms, and entire marine food webs. At the same time, warmer waters hold less oxygen, which creates dead zones where life struggles to survive. These aren't distant or theoretical problems. They're happening now in places where fisheries collapse and coral bleaches white in heat-stressed waves. Even the very air we breathe can be affected. Climate change increases the frequency of wildfires, which fill the sky with particulate matter and soot. It alters pollen seasons and worsens respiratory conditions. Ozone, beneficial in the upper atmosphere, becomes harmful when it builds up near the ground, contributing to smog and asthma. In some cities, air quality is already a daily concern. In a warming world, that concern spreads. But amid all this complexity, there's something else that deserves attention: the role of life itself in regulating the atmosphere. It's not just that trees and algae create oxygen, it's that the biosphere as a whole helps stabilise the planet. From microbial life in the soil to plankton in the oceans, living systems constantly respond to environmental changes, buffering extremes, recycling nutrients, and sequestering carbon. That response isn't limitless, but it is resilient. In many cases, ecosystems can bounce back if given the chance. That's part of the puzzle we're trying to solve now. How much damage is too much? How close are we to thresholds beyond which recovery becomes impossible? In climate science, these are called tipping points, moments when small changes trigger larger, often irreversible shifts. The collapse of the Amazon rainforest, for example, could release massive amounts of stored carbon and turn the region from a carbon sink into a carbon source. The melting of the Greenland ice sheet could disrupt ocean currents and change weather patterns across continents. These aren't just local problems. The atmosphere, after all, doesn't recognise borders. There's also the question of time. Climate change is often described as a slow-moving crisis, but in geological terms it's happening at breakneck speed. Atmospheric CO2 hasn't risen this fast in millions of years. Species are going extinct at rates not seen since the last mass extinction event. The Earth can adapt, but not always at the pace we're changing it. And when adaptation can't keep up, systems fail. Still, it's not all loss. The atmosphere, for all its delicacy, is also a system we understand surprisingly well. We've sent balloons and satellites to measure it. We've built models to simulate its behaviour. We've identified the gases, the layers, the processes that keep it in motion. And we've found ways to intervene. Reforestation, clean energy, carbon capture. None of these are magic solutions, but they are part of a larger effort to slow the damage, and in some cases even reverse it. But understanding is not the same as acting. The science is clear. The atmosphere is warming. Carbon levels are rising. Human activity is the driver. And without a change in course, the systems that once made this planet feel like home could begin to falter in ways we can't easily undo. Even so, the air remains, still breathable, still soft on the skin, still full of wind and bird song and clouds that curl and vanish. The atmosphere is not yet lost. It moves above us constantly, brushing mountaintops, stirring oceans, wrapping the earth in invisible rhythm. And every time you breathe, you are part of it. A tiny, pulsing thread in the fabric of a living planet. In the space between that breath and the next, there is still time to change. The air we breathe may be invisible, but we feel its movement constantly. In the sway of trees, the chill of a breeze, the weight of humidity before a storm. We know the sky not just by colour or light, but by how it behaves. For most of our lives, weather has been something we respond to with casual preparation. Bring a jacket, carry an umbrella, check the forecast. It's a background rhythm, a thing that shifts, but usually within the range of what we consider normal. But that sense of normal is changing. What we call weather is really the atmosphere in motion. Heat from the sun unevenly warms the Earth's surface, and that heat drives winds, clouds, rain, and temperature swings. The equator receives more sunlight than the poles, creating pressure differences that move air and water around the planet. The rotation of the Earth adds spin to these movements, shaping trade winds and ocean currents. Mountains, forests, deserts, and coastlines all contribute to the patterns. It's a dynamic system full of variation. But behind the chaos, there's usually a kind of order. Seasons, climate zones, predictable extremes. Climate, by contrast, is the average of that weather over time. When people talk about climate change, they're not talking about the rain tomorrow or next week's cold snap. They're talking about long-term shifts in patterns, warmer winters, earlier springs, longer droughts, stronger storms. These shifts aren't just numbers on a graph. They ripple into real life through the weather we notice every day. And increasingly the weather is turning fierce. Heat is one of the most direct and visible symptoms. The past decade has seen record-breaking temperatures around the world, with some regions experiencing deadly heat waves that stretch for days or weeks. In places where air conditioning is scarce or the grid is unreliable, extreme heat becomes a serious health threat. Elderly people, outdoor workers, children, and those with pre-existing conditions are especially vulnerable. It's not just uncomfortable, it's dangerous. And the frequency of these events is rising. High temperatures also have indirect effects. Crops wither in the heat, reducing yields and putting pressure on food supplies. Roads buckle, train tracks warp, and infrastructure strains under loads it wasn't built to handle. Wildfires, already a natural part of some ecosystems, become more intense and harder to control. Drier vegetation provides more fuel. Lightning strikes become ignition points, and once fires start, they create their own weather. Updrafts, gusts, even firestorms that mimic the behaviour of hurricanes. On the other end of the water spectrum, storms are becoming stronger. A warmer atmosphere holds more moisture, and that moisture supercharges rainfall. Hurricanes and typhoons feed off warm ocean water, and as sea surface temperatures rise, these storms grow more powerful. They form more rapidly, last longer, and drop more rain. Storm surges become higher. Floodplains stretch farther. In some areas, the frequency of storms isn't increasing, but their intensity is. Flooding is another growing concern. Some of it comes from heavy rainfall, where storms dump more water than the ground can absorb. Some comes from snowmelt, where warmer winters create a faster thaw. And some comes from sea level rise, which pushes tides farther inland. Even places that didn't consider themselves flood-prone are seeing streets submerged and homes damaged. Insurance systems struggle to keep up. Recovery becomes harder each time. Meanwhile, other regions face the opposite problem: drought. Changing weather patterns can shift rainfall away from areas that depend on it, leaving soils dry and rivers low. Agriculture suffers, reservoirs drop, wildfire risk climbs. In some places, droughts come in long, slow waves, creeping in so gradually they're only recognised in hindsight. In others, they arrive suddenly, forcing rationing, water restrictions, and hard choices about what to grow or where to live. It's not just the extremes that are changing. The transitions between seasons are shifting too. Spring arrives earlier, snow melts sooner. Insects emerge before the birds that feed on them. Crops bloom out of sync with pollinators. These small misalignments matter. Over time, they accumulate. Ecosystems that once moved in harmony begin to fall out of rhythm. Jet streams, the fast-moving rivers of air high above the surface, are also changing. These currents help guide weather systems across continents. But warming in the Arctic has reduced the temperature difference between the poles and the equator, which weakens the jet stream. A weaker jet stream becomes more wobbly, causing weather systems to linger. That's part of why some areas experience extended heat waves, prolonged rain, or repeated cold spells. The systems aren't necessarily more frequent, but they stick around longer, doing more damage. And as the climate changes, old records don't hold. What was once a 1-in-1,000-year flood might now happen every few decades. What used to be a rare heatwave becomes a routine summer feature. Infrastructure built for the old normal begins to falter under the weight of the new. Storm drains overflow. Power grids sag under demand. Buildings overheat. Emergency services stretch thin. Adaptation becomes less about preparation and more about catching up. For many, the changes show up slowly. A few degrees hotter each summer, a few more storms each year. But for others, the impact is immediate and severe. Island nations face rising seas. Coastal cities spend billions on seawalls and pumps. Farmers plant different crops or abandon fields entirely. Some communities relocate altogether, others can't. Climate change doesn't create storms from nothing. It amplifies the ones that were already going to happen. A heat wave becomes a deadly event. A storm becomes a disaster. A dry season turns into a drought. This amplification effect is one of the most consistent findings across climate research. The physics is well understood. The outcomes, though, vary by location, which makes adaptation tricky. What works in one place may not work in another. There are also the less visible consequences. The emotional and psychological toll of extreme weather is real. Disasters disrupt communities, displace families, and create long-term stress. People who survive wildfires or floods often struggle with anxiety, depression, or grief. Rebuilding isn't just about bricks and roads. It's about trust, memory, and a sense of safety. As the sky grows more volatile, questions arise about how much warming we can handle before parts of Earth become difficult, or impossible, to live in. The concept of wet bulb temperature comes into play here. It combines heat and humidity into a single number, representing the point at which the human body can no longer cool itself through sweating. At a wet bulb temperature of around 35 degrees Celsius, even healthy people in the shade with water to drink can die after prolonged exposure. Some regions, especially in South Asia and the Middle East, are already approaching these limits during heat waves. These aren't future projections, they're measurable shifts, happening now in places people call home. And while the world is working to slow these changes, through emissions reductions, renewable energy and improved forecasting, the weather doesn't wait. It moves on its own schedule. Still, understanding the patterns helps. Better data, better models, and better communication mean that we can prepare earlier, respond faster, and recover more effectively. Cities are redesigning streets to manage heat. Forests are being managed to reduce fire risk. Floodplains are being restored to absorb water. These adaptations aren't enough on their own to stop the warming, but they can buy time and protect lives. Weather has always been a part of the human story. It shapes where we settle, what we grow, how we build. But now, as the sky grows louder and less predictable, it asks more of us. Not just to endure the storms, but to understand what's changing and why. We're not just passengers in this system, we are participants. The carbon we emit, the land we use, the choices we make, they feed back into the sky. The storms that rise over oceans, the heat that builds in cities, the rain that falls too hard or not at all, they're connected to us. And so, the question continues to unfold. Not just whether Earth will remain habitable, but which parts will, and for how long, and what that means for where we live, how we live, and who gets to decide. From here, the path leads deeper into the systems we depend on, into the oceans that are rising and warming, the currents that carry life, and the slow but steady march of sea toward land. There's more to come. If you've ever used a kitchen timer or watched a kettle slowly come to boil, you know how easy it is to underestimate a gradual build-up until it crosses a threshold and can't be ignored anymore. Climate works a bit like that. It builds quietly, almost invisibly, while the world carries on with its daily noise. Then one day a warning arrives, and it's not just a number on a chart. It's a flooded street, a failed harvest, or a day too hot to work outside. These are the signals of a system that has been absorbing pressure for decades, and a big part of that pressure comes down to carbon. Carbon dioxide isn't the only greenhouse gas, but it's the most talked about for a reason. It's the most abundant among the ones humans are adding to the atmosphere, and it stays there the longest, for centuries in some cases. That makes it more than just a short-term issue. Every tonne emitted now becomes part of the climate decades from now, and the carbon clock keeps ticking. When fossil fuels like coal, oil and natural gas are burned for energy, they release carbon that's been locked underground for millions of years. That carbon had been out of circulation, safely stored in rock and sediment. Releasing it is like opening an old vault that was never meant to be touched. And the moment we started doing that, during the Industrial Revolution, the atmospheric concentration of CO2 began to rise at a pace unmatched in geological history. In 1958, a scientist named Charles David Keeling began measuring carbon dioxide levels from an observatory on Mauna Loa in Hawaii. That data set, known now as the Keeling curve, was the first direct evidence of what scientists had suspected. The atmosphere was changing. The curve showed not only that CO2 levels were increasing, but that they were doing so year after year, with seasonal fluctuations from plants absorbing and releasing carbon. But the overall trend was unmistakable, an upward slope that has continued ever since. The numbers tell a clear story. For most of human history, CO2 levels hovered around 280 parts per million. By the early 2000s, they had passed 370. As of today, they've climbed beyond 420, and they show no signs of slowing. These may seem like small numbers, but in climate systems, even slight shifts can have far-reaching effects. The last time CO2 levels were this high, sea levels were several meters higher and temperatures were several degrees warmer. Humans didn't exist yet, and it's not just CO2. Methane, another greenhouse gas, is even more potent in the short term, over 80 times more effective than CO2 at trapping heat over a 20-year period. It comes from natural gas leaks, livestock, rice fields, landfills, and thawing permafrost. Its concentrations have more than doubled since pre-industrial times. Then there's nitrous oxide, released from fertilizer use and industrial activity. It's less talked about, but equally important, with a warming potential nearly 300 times that of CO2 over a century. Each of these gases contributes to what's called radiative forcing, the difference between the energy Earth receives from the sun and the energy it radiates back into space. Greenhouse gases trap some of that outgoing energy, warming the planet. The more we emit, the more heat is retained. This is not a theory or a guess, it's measurable. It's been observed in satellites, weather stations, and climate models around the world. There's a concept in climate science known as carbon budget. It's a way of thinking about how much CO2 we can still emit before crossing certain temperature thresholds. The most commonly cited targets are 1.5 and 2 degrees Celsius of warming above pre-industrial levels. These aren't random figures. They represent limits beyond which the risk of triggering dangerous and irreversible climate impacts becomes significantly higher. More extreme heat, more sea level rise, more ecological collapse. According to the best available estimates, humanity has already used up most of the budget for staying below 1.5 degrees. What's left is small and shrinking. Every year of high emissions makes the remaining space smaller, and while 2 degrees might sound close to 1.5, the impacts grow quickly with each fraction of a degree. More coral reefs lost, more days of deadly heat, more displacement of people from low-lying areas. But emissions don't come evenly from all sources. Some sectors are responsible for more than others. Energy production, especially electricity and heat from fossil fuels, is the largest contributor. Transportation, particularly cars, trucks, ships and planes, adds another major slice. Industry, agriculture and buildings round out the rest. And within those sectors there are solutions. Cleaner fuels, better efficiency, less waste, smarter design. But implementing those solutions takes time, money and political will. Carbon dioxide removal is another approach getting more attention. These are technologies and practices that pull carbon back out of the atmosphere. Reforestation is the most well known. Trees absorb carbon as they grow and store it in wood and soil. Other methods include soil carbon sequestration, where farming practices help store carbon underground, and direct air capture, which uses machines to extract CO2 from the air and store it. There's also bioenergy with carbon capture and storage, burning plant material for energy, and capturing the emissions before they reach the atmosphere. These ideas are promising, but they're not silver bullets. Many of them are still expensive or difficult to scale, and most scientists agree that removing carbon, while necessary, is not a substitute for reducing emissions. It's not enough to mop up the floor while the tap is still running. Some emissions are harder to avoid. Certain industrial processes, like making steel or cement, currently produce CO2 as a byproduct. Aviation and shipping are difficult to electrify. Agricultural emissions, especially methane from livestock and nitrous oxide from fertilizers, don't have easy substitutes. But even these sectors are seeing innovation. Alternative fuels, lab-grown meat, regenerative farming. These are all part of the broader toolkit. Still, the core message remains. The clock is ticking. The longer emissions stay high, the harder it becomes to stay within the safe limits. And unlike some problems, climate change doesn't stop the moment we reduce the cause. The gases already in the atmosphere will continue to warm the planet for decades. That's what makes timing so crucial. There's also the issue of fairness. Countries that contributed the most to historical emissions are often not the ones suffering the worst effects. Small island nations, low-income communities and regions already vulnerable to drought or heat have the least capacity to adapt. Meanwhile, wealthier countries with higher past emissions have more resources to protect themselves. Better infrastructure, stronger health systems, more political stability. That imbalance shapes global negotiations. Climate talks, like those under the United Nations Framework Convention on Climate Change, try to address these disparities by encouraging wealthier nations to finance adaptation and mitigation efforts elsewhere. But progress is slow, promises are made, some are kept, some aren't. Despite all of this, the signs of potential progress are real. Many countries are investing in renewable energy at record levels. Solar and wind are now cheaper than fossil fuels in many parts of the world. Electric vehicles are becoming more common. Cities are updating building codes to reduce emissions. Businesses are setting climate targets. Individuals are reducing waste, conserving energy, and choosing more sustainable options. Each step helps, but they must add up fast enough to change the curve. It can be hard to stay hopeful when the numbers keep rising. But the carbon clock is not a countdown to doom. It's a tool. It shows how much time we have left to change course, not just for policymakers, but for everyone. The choices made in the next few years will shape the kind of planet future generations inherit. And if that sounds heavy, it's because it is. But weight doesn't have to mean despair. It can also mean clarity, a shared understanding of what matters and what's possible. The atmosphere isn't a lost cause. It's a system that responds to action. The same feedback loops that can accelerate damage can also amplify recovery. If emissions fall, if forests grow, if systems shift. The clock is ticking, but it hasn't run out. If you were to stand on a beach and look out across the water, you might not think of the ocean as moving. Waves come in, waves go out. Tides rise and fall with familiar rhythm. But beyond what we can see from the shore, the ocean is in constant motion, deep, wide, powerful, and quietly shaping the climate of the entire planet. Covering more than 70% of Earth's surface, the ocean is one of the most important systems for regulating temperature, storing energy, and moving heat around the globe. It absorbs about 90% of the excess heat trapped by greenhouse gases, acting as a buffer against rapid atmospheric warming. Without it, the air would be much hotter, and the climate would be far more volatile. But that service comes at a cost. Warm water expands, and as the ocean's heat, sea levels rise. Melting ice adds more water to the mix. Together, these effects push coastlines farther inland. The rise isn't uniform. Local conditions, currents, and even gravity can make sea levels change more in some places than others. But the overall trend is clear. Seas are rising slowly but steadily, and in some places the land is sinking at the same time, compounding the effect. Coastal communities are already seeing the results. High tides reach farther. Floods that used to come once a decade now arrive every year or two. Salt water seeps into freshwater supplies and agricultural land. In some places the changes are measured in centimetres. In others, they're measured in the number of times people have had to rebuild. Then there are the currents. Vast rivers within the sea, moving warm and cold water across continents. These currents play a vital role in regulating global climate. The Gulf Stream, for example, carries warm water from the tropics to the North Atlantic, keeping much of Europe milder than it would otherwise be at those latitudes. In the southern hemisphere, the Antarctic circumpolar current loops uninterrupted around the globe, connecting oceans and helping regulate heat and carbon flow. These currents are driven by a combination of wind, Earth's rotation, and differences in temperature and salinity, a process called thermohaline circulation. Cold, salty water is denser and sinks, pulling warmer water toward the poles to replace it. This conveyor-like system helps stabilise the climate by distributing energy across the planet. But it's slowing down. Research shows that parts of this global ocean conveyor are weakening, particularly in the North Atlantic. Fresh water from melting Greenland ice is reducing salinity and disrupting the sinking motion that drives the current. If this continues, it could have far-reaching effects, altering weather patterns, changing rainfall distribution, and raising sea levels along parts of the US East Coast and Western Europe. The last time this system weakened significantly was during the end of the last ice age, and it caused abrupt climate shifts. In addition to moving heat, the ocean also stores a large portion of the carbon dioxide released into the atmosphere. Phytoplankton, tiny plant-like organisms near the surface, absorb CO2 during photosynthesis. When they die, some of that carbon sinks into the deep ocean, effectively storing it for centuries. But as ocean temperatures rise and acidity increases, this process becomes less efficient. Ocean acidification is another issue with global reach. When CO2 dissolves in seawater, it forms carbonic acid, which lowers the water's pH. This affects organisms that build shells and skeletons out of calcium carbonate, including corals, oysters, clams, and many types of plankton. The more acidic the water becomes, the harder it is for these organisms to grow and survive. And because they're often near the bottom of the food web, their decline can ripple upward, affecting fish, birds, and even people who rely on seafood. Nowhere is the impact of warming and acidification more visible than in coral reefs. These ecosystems, often called the rainforests of the sea, support an extraordinary range of life. They provide food, shelter, and breeding grounds for countless marine species. They also protect coastlines from storm surge and erosion. But corals are sensitive. When water becomes too warm, they expel the algae that live inside them. Algae that provide energy and colour. This leads to coral bleaching. If the heat continues, the coral dies. In recent decades, mass bleaching events have become more common, affecting large stretches of reef around the world, including Australia's Great Barrier Reef. Recovery is possible if conditions improve, but repeated or prolonged stress can push reefs beyond their limits. Some are already transitioning into different ecosystems, less diverse, less vibrant, less capable of supporting the species that once depended on them. Deeper in the ocean, far from sunlight, other changes are unfolding. As the surface warms, it creates a more stable barrier between layers of water. That makes it harder for oxygen from the surface to mix into deeper layers. Oxygen levels are dropping in many parts of the ocean, creating zones where few organisms can survive. These low oxygen areas, sometimes called dead zones, are also fueled by nutrient runoff from agriculture. Fertilizers wash into rivers, rivers flow into oceans, and algae blooms follow. When the algae die and decompose, they consume oxygen, leaving behind anoxic water. These processes are complex and interconnected. Warming, acidification, deoxygenation, and pollution interact in ways that are difficult to predict in detail. But the overall direction is clear. Marine ecosystems are under stress, and as they struggle, so do the people who depend on them. More than 3 billion people rely on fish as a major source of protein. Many coastal economies depend on tourism, fisheries, and marine trade. When the ocean changes, those livelihoods are affected. Fish migrate to cooler waters, catches decline, coral loss reduces tourism. Ports need to be redesigned to handle higher sea levels and more frequent storm surges. Some efforts are underway to adapt. Marine protected areas are expanding, giving ecosystems room to recover. Sustainable fishing practices are becoming more common in some regions. Coastal cities are building seawalls, restoring wetlands, and creating buffer zones. But like most climate adaptation, these efforts must move quickly to keep up with the rate of change. There's also growing interest in restoring ecosystems that act as natural climate solutions. Mangroves, salt marshes, and seagrass beds capture and store large amounts of carbon. They also protect coastlines from erosion and storm damage. Rebuilding these habitats can be both a climate strategy and a biodiversity one. But restoration takes time, and not all damage can be undone. Some of the changes now underway may be with us for centuries. Sea level rise in particular is difficult to reverse. Even if all emissions stop tomorrow, thermal expansion and melting ice would continue to add water to the oceans for a long time. That's not a reason for despair. It's a reminder of how important the present moment is. Every tenth of a degree matters. Every year of delay adds to the future challenge. It's easy to think of the ocean as a separate world, vast, deep and distant. But it touches everything. It shapes weather, regulates temperature, provides food, absorbs carbon and sustains life. It moves constantly, even when we're not watching. And now, it's moving faster in directions that ask more of us. The tide is rising, but it hasn't crested. What happens next depends on how we respond, not just to the water, but to the systems we've built beside it. Cities, ports, economies, communities, all connected to a sea that is warmer, fuller, and more restless than it was a century ago. And so we look ahead to what else is changing, to the forests that shape rainfall, the soils that feed billions, and the ecosystems that still hold pieces of the balance. We'll follow the path inland now, where trees, crops, and the ground beneath our feet tell their own part of the story. Not all climate stories begin with weather maps or carbon charts. Some begin beneath your feet. If you've ever dug your hands into dark, rich soil, walked through a forest after rain, or stood at the edge of a farm at harvest time, you've seen parts of the planet that hold more than just life. They hold balance. And for all our focus on emissions and energy, the ground still matters. A great deal more than most people realise. Soil isn't just dirt. It's alive. A complex structured environment made up of minerals, organic matter, air, water, fungi, bacteria, and countless tiny organisms. A single handful can contain more microbes than there are people on Earth. This hidden world beneath the surface plays a central role in food production, water retention, carbon storage, and ecosystem stability. It anchors plants, filters water, recycles nutrients, and feeds the base of nearly every terrestrial food web. When it's healthy, it does all of that quietly, reliably. When it breaks down, the consequences ripple outward. Agriculture relies on soil that can hold moisture, drain well, resist erosion, and support plant growth. But farming also exerts pressure. Intensive tillage, monoculture planting, synthetic fertilizers, and overuse of pesticides can degrade the structure and microbial life of soil. Over time, this leads to compaction, nutrient loss, and increased vulnerability to drought and flood. In some regions, fertile land has turned to dust, and farming becomes harder with each season. This degradation has a climate dimension too. When soil loses organic matter, the carbon-rich material made of decayed plants and animals, it also loses the ability to store carbon. Disturbed soil releases carbon dioxide into the atmosphere, accelerating warming. That warming then feeds back into more frequent droughts and extreme weather, which further degrade the soil. It's a cycle that builds slowly, but with real weight. There are ways to reverse the trend. Practices like no-till farming, cover cropping, composting, and crop rotation can rebuild organic matter and restore microbial diversity. These approaches fall under the umbrella of regenerative agriculture, a system designed not just to minimize harm, but to actively improve the land. Some farmers are already seeing benefits: better yields, more drought resilience, lower input costs. But adoption varies, and scaling these changes takes time, support, and policy shifts. Forests also play a central role in maintaining Earth's balance. They cover about 30% of the planet's land area and serve as carbon sinks, water regulators, climate stabilizers, and biodiversity havens. Trees absorb carbon dioxide during photosynthesis, store it in wood and soil, and release oxygen back into the air. A mature forest is more than just a collection of trees. It's an interconnected system of roots, fungi, animals, and microbes, all working together in a kind of slow organic choreography. Tropical forests like the Amazon, the Congo Basin, and Southeast Asia's rainforests are especially important. They hold massive amounts of carbon and moisture, influence global rainfall patterns, and host a huge share of the planet's biodiversity. But they are also under pressure. Deforestation, driven by logging, agriculture, mining, and infrastructure, continues at a scale that's difficult to fully track in real time. When forests are cleared or burned, the carbon stored in their biomass is released, turning them from carbon sinks into carbon sources. In the Amazon, researchers have found signs that parts of the forest may be approaching a tipping point. As rainfall patterns shift and temperatures rise, some areas are drying out, burning more often, and becoming less able to regenerate. If this trend continues, the forest could begin transitioning into a savanna-like state, with lower carbon storage capacity and reduced biodiversity. That shift would have global consequences, not just regional ones. Outside of the tropics, boreal forests, stretching across Canada, Scandinavia and Russia, also store vast amounts of carbon, much of it in their soils. But these forests are increasingly vulnerable to wildfires, insect outbreaks and warming temperatures. Fires in boreal regions release not only the carbon in trees, but also carbon from deep soil layers, especially peat, which burns slowly and is difficult to extinguish. As the planet warms, these fires are becoming more frequent and harder to control. Planting trees is often promoted as a solution, and in some contexts it can help. But not all tree planting efforts are equally effective. Planting non-native species, monocultures or trees in ecosystems that weren't originally forested can harm biodiversity, alter water cycles, and displace local communities. Reforestation and afforestation are most effective when they restore native species, support local ecosystems, and are integrated with other land use priorities. Meanwhile, the balance between agriculture and forested land is becoming more strained. As the global population grows and diets shift, more land is cleared for crops and livestock. About 80% of the world's farmland is used to produce meat and dairy, even though those foods account for less than 20% of global calories. Reducing food waste, improving yields on existing farmland, and shifting dietary patterns, even slightly, can reduce pressure on forests and free up land for rewilding or conservation. There's also the question of land tenure. Who owns the land? Who controls it? And whose interests are prioritised? Indigenous communities manage or protect a significant portion of the world's remaining forests and biodiversity hotspots. Research shows that where Indigenous land rights are recognised, deforestation rates are often lower, and ecosystems are better maintained. Yet these communities often face legal, political and economic pressures that undermine their stewardship. Even small ecosystems hold outsized influence. Grasslands, wetlands, savannas. Each plays a role in storing carbon, cycling water, and supporting life. Wetlands in particular are powerhouses of carbon storage, filtering water and buffering coastlines. But like forests, they've been drained, filled, or degraded in many regions, especially for development and agriculture. So the land beneath us holds a kind of quiet leverage. Soil, forests and farms are not just passive backgrounds to the climate story. They're active players. They absorb, release, adapt, and transform. And because they operate on human scales, meters instead of atmospheres, seasons instead of centuries, we have a real chance to influence them. Technology can help. From satellite monitoring of deforestation to precision agriculture that reduces fertilizer use. Policy helps too, with subsidies that support sustainable practices, incentives for conservation, and trade rules that discourage environmental harm. But much of the work is practical and grounded. It happens on farms, in forests, in the hands of people planting, tending, harvesting, and protecting. As the climate changes, some land will become less productive. Droughts, heat waves, floods, and shifting pests will all challenge traditional farming. But land can also be a part of the solution, storing more carbon, producing food more efficiently, and restoring ecosystems that have been damaged. There's no single fix, But there is momentum. Regenerative agriculture is growing. Forests are being protected. Wetlands are being restored. And the knowledge needed to do these things well is not new. In many cases, it's being recovered from traditional farming methods, local observation, and long-practiced land stewardship. The path forward won't be easy, but it is visible. The seeds of change are already there, in the way we grow food, in how we care for soil, in the forests that still stand, and in those that might return. They're in the decisions being made now, quietly, across fields and hills and wooded edges, decisions that shape not just the land but the air, the water, and the climate that surrounds us all. When we talk about extinction, the mind often drifts to the dinosaurs, creatures so distant in time they feel almost like myth. Their sudden disappearance, tied to an asteroid impact and cascading planetary shifts, is the most famous extinction event in Earth's history. But it wasn't the first, or even the worst. In the last 500 million years, Earth has experienced 5 major mass extinctions, moments when the pace of species loss far outstripped normal background rates, reshaping the tree of life each time. Today, there's growing evidence that we're entering a 6th. Extinction is a natural part of life. Species emerge, adapt, evolve, and eventually disappear. But under typical conditions, this happens slowly. A few species lost here and there over centuries or millennia. What defines a mass extinction is not just the number of species lost, but how quickly it happens and how broadly it cuts across ecosystems. It's a compression of time, a sharp drop in biodiversity that leaves the world noticeably emptier. Right now, species are disappearing at rates estimated to be between 100 and 1,000 times higher than normal. That doesn't mean mass die-offs are happening daily. It means that the background hum of extinction has grown louder, more constant and harder to ignore. Many scientists now believe we are living through the early stages of the 6th mass extinction, one driven not by volcanic eruptions or asteroid impacts, but by human activity. The causes are well known. Habitat destruction is the leading driver. As forests are cleared, wetlands drained and grasslands ploughed, the spaces where wildlife once thrived disappear or fragment. Even when some land remains, it may be cut off by roads, surrounded by farms, or too degraded to support the species that once lived there. Pollution plays its part too. Pesticides, heavy metals, plastics, and runoff from agriculture all enter ecosystems and alter the delicate chemistry of life. Oceans absorb excess carbon and become more acidic. Rivers pick up nutrients that fuel harmful algal blooms. Air carries particulate matter that changes everything from insect behaviour to respiratory health in mammals. Then there's overexploitation, the hunting, fishing and harvesting of species faster than they can reproduce. Some of this is industrial, some of it is local and subsistence-based, some of it feeds international demand. The result is the same. Populations decline, reproductive patterns break, and once common animals begin to vanish. Invasive species add another layer. As humans move around the world, they bring other organisms with them, intentionally or not. Rats arrive on ships, insects hitch rides and cargo. Plants are introduced as ornamentals and take over. Many introduced species fail to thrive, but some flourish and outcompete native ones, shifting the balance of ecosystems. The damage isn't always dramatic. Sometimes it's subtle, long-term, a slow reshuffling of who lives where, until something critical is lost. And finally, climate change. Rising temperatures, shifting seasons, and altered weather patterns are forcing species to move, adapt, or die. Some can shift their ranges, others can't. Some can evolve quickly. Others are too specialised, too slow, or already weakened by other threats. As habitats change, so do food sources, migration routes, and reproductive windows. The result is a growing mismatch between what species need and what their environments can now provide. Certain groups are more vulnerable than others. Amphibians, frogs, toads, salamanders are especially sensitive to environmental changes. Many are already endangered. Insects, often overlooked, are seeing widespread declines in abundance and diversity. Birds that rely on specific migration routes or habitats are struggling to keep pace with a changing world. Coral reefs, as discussed earlier, are bleaching and dying, and larger animals, from elephants to whales, face a mix of poaching, habitat loss, and slow reproduction that puts them at risk. But extinction isn't just about individual species, it's about the networks they're part of. Every organism fits into a larger system. Plants feed insects, insects pollinate crops, birds control pests, predators keep prey populations in balance. When one piece disappears, others shift to fill the gap, but there are limits. If too many species vanish, the web begins to fray. Biodiversity provides resilience. Ecosystems with many species can better absorb shocks, adapt to changes, and recover from disturbances. They support clean water, fertile soil, pollination, and disease regulation. When that diversity erodes, ecosystems become more brittle, more likely to collapse when stressed. The idea of a sixth mass extinction isn't just academic. It has consequences for people. Our food systems rely on pollinators. Our medicine comes from natural compounds. Our economies depend on stable ecosystems. And beyond practical needs, there's a sense of shared heritage, a recognition that we are part of something much larger, more complex and more beautiful than ourselves. The loss of species diminishes not only the natural world, but also our understanding of it. Still, there are reasons to be cautious with language. Not every scientist agrees on the timeline or severity. Some argue we haven't crossed the threshold yet, that current rates, while alarming, are still below the levels seen in past mass extinctions. Others say we're in the early phase, and the worst is yet to come. Either way, the direction of change is clear. Species are declining, habitats are shrinking, pressures are mounting. There are also reasons for hope. Conservation works. Protected areas can stabilize populations. Habitat corridors help species migrate. Captive breeding programs have saved animals from the brink. International agreements like CITES help regulate trade in endangered species. Local communities, indigenous groups, and citizen scientists all contribute in ways that are often underreported. The global effort to catalogue life is growing too. With new technologies, researchers are discovering species faster than ever before. Some are tiny, microbes, fungi, insects. Some are large, birds, mammals, deep-sea creatures. Many remain unnamed. By understanding what's out there, we have a better chance of protecting it. Efforts are also shifting from protecting single species to preserving entire ecosystems. This approach recognizes that no creature exists in isolation. Forests, reefs, wetlands. These are the true units of conservation. They support not just wildlife, but also the human communities that depend on them. In recent years, terms like rewilding and restoration have entered the conversation. These are efforts not just to preserve what's left, but to bring back what was lost, to reintroduce species, rebuild ecosystems, and allow nature more space to heal. These projects are complex and sometimes controversial, but they offer a different frame, not just fighting loss, but rebuilding abundance. The sixth mass extinction, if it continues, won't happen in a single moment. It will unfold across years and lifetimes, a gradual erosion that becomes more visible the longer it goes on, but that also means there is time. Not unlimited time, not time to waste, but time enough to change course. It starts with recognizing the value of biodiversity, not just as a set of names on a list, but as the living foundation of the systems that sustain us. It requires attention, coordination, and humility. And it asks whether a world quieter in birdsong, emptier of forests, and lonelier in the wild can truly be called habitable. From here, the question turns again. to the things we build, the machines we rely on, and the systems that keep our world running. Technology shapes the planet now as much as nature once did, and its shadow, as well as its promise, reaches into every corner of the climate story. For most of human history, survival was a matter of adapting to nature. Weather, seasons, predators, soil. We learned to observe, predict, and work within the limits of the environment. But with time came tools, and with tools came machines. Eventually we began to shape the world around us more than it shaped us. And now, much of what we consider modern life, electricity, transportation, communication, food systems, clean water, depends on technology that operates quietly in the background, often unnoticed until something goes wrong. These machines have done extraordinary things. They've extended lifespans, shrunk distances, connected billions of people, and made everyday survival more predictable. We've harnessed energy from coal, oil, gas, atoms, wind, sun, and water. We've built roads, satellites, networks, and cities. But every step of that progress has carried a footprint, a cost that's often paid in emissions, extraction, waste, and imbalance. It starts with energy. The Industrial Revolution was powered largely by coal, followed later by oil and natural gas. These fossil fuels offer dense, transportable, and reliable energy, a kind of stored sunlight from ancient organisms compressed by time. Burning them made large-scale manufacturing, transport, and electricity possible. It also began releasing vast amounts of carbon dioxide into the atmosphere. Modern machines, as cars, planes, factories, power plants, run on this energy. Globally, about 80% of the world's energy still comes from fossil fuels. Each stage of that energy use, extraction, refining, transport, combustion, contributes to greenhouse gas emissions. Some of those emissions are direct. Others come from the indirect systems that support the infrastructure. Concrete for roads, steel for vehicles, plastics for packaging. Transportation alone accounts for a significant share of emissions. Personal vehicles, freight trucks, ships, and airplanes all rely heavily on oil. Electric vehicles are growing in number, but the transition is far from complete. Aviation and shipping remain difficult to electrify at scale. The supply chains that deliver goods to homes and businesses are built on a foundation of fossil energy. Industry contributes in different ways. Cement production, for example, releases carbon dioxide as a byproduct of the chemical reaction that turns limestone into lime. Steel production requires extremely high heat, often provided by coal. These processes are foundational to infrastructure worldwide. Bridges, buildings, power lines, ports, and alternatives, while emerging, are still expensive or in early development. Technology has also changed agriculture. Tractors, irrigation systems, synthetic fertilizers, pesticides, all have boosted productivity and helped feed billions. But they've also increased emissions, degraded soil, and contributed to water pollution. Fertilizer use releases nitrous oxide, a potent greenhouse gas. Machinery runs on fuel. Clearing land for agriculture, particularly in tropical regions, contributes to deforestation, reducing carbon sinks. At the same time, technology has enabled massive cooling systems, air conditioning, refrigeration, and data centers, all of which require energy and often rely on refrigerants with high global warming potential. These technologies improve health, safety, and convenience, but they also create additional pressure on power grids, especially in hotter climates where cooling becomes essential rather than optional. Digital technology brings its own complexities. The devices we use daily, smartphones, laptops, routers, require rare earth metals, mined in energy-intensive processes that often carry environmental and social costs. Data storage and cloud computing, while invisible to users, rely on server farms that consume vast amounts of electricity. As digital infrastructure expands, so does its environmental footprint. Then there's waste. Not just emissions, but physical byproducts. E-waste from discarded electronics. Plastic from packaging and manufacturing. Chemical runoff from industrial processes. These materials often accumulate in landfills, waterways and oceans. Many are persistent, meaning they don't break down easily, and some are toxic to ecosystems and humans alike. Despite all this, technology also offers tools to address the problems it helped create. Renewable energy is growing rapidly. Wind, solar and hydro are providing clean electricity at scales once thought unrealistic. Battery storage is improving. Smart grids are helping balance supply and demand. Electric vehicles are becoming more efficient and charging networks are expanding. There are also innovations in energy efficiency, from better insulation and lighting to improved industrial processes. In many cases, saving energy also saves money, which accelerates adoption. Buildings are being designed to use less heat and air conditioning. Appliances are becoming more efficient. Cities are using data to manage traffic, reduce waste, and optimize public transit. Carbon capture technologies are being developed to remove carbon dioxide from the air or from power plant exhaust. Some of these use chemical scrubbing. Others rely on enhanced mineral weathering or bio-based approaches. These systems are expensive and not yet widely deployed, but they could play a role in reaching net zero emissions, especially for sectors that are hard to fully decarbonize. Technology is also helping track and model environmental change. Satellites monitor deforestation, ice melt, and sea level rise. Sensors collect data on air and water quality. Machine learning algorithms analyze trends and improve forecasting. This information helps governments, businesses, and communities plan more effectively, from early warning systems for storms to smarter crop management. In agriculture, precision techniques are reducing water and fertilizer use. Drones monitor crop health. Automated irrigation adjusts to real-time conditions. Vertical farms and lab-grown meat offer new models for food production with smaller footprints. These tools are not yet accessible everywhere, but they point toward more efficient and sustainable systems. Even construction is evolving. New materials like low-carbon cement, engineered timber, and recycled steel are entering the market. 3D printing is being explored for reducing waste in building. Modular designs allow for easier upgrades and repurposing. Retrofitting existing buildings for energy efficiency often costs less than replacing them and avoids the emissions embedded in new construction. Still, for all the advances, technology alone can't solve the problem. Many of the emissions come not just from how machines are built or powered, but from what we ask them to do, how often we drive, what we consume, how much we waste. Changing that means addressing behavior, systems, and expectations. There are trade-offs too. Mining for lithium, cobalt, and other battery materials can damage ecosystems and create new dependencies. Solar panels and wind turbines require land, raw materials, and long-term disposal plans. Building clean energy infrastructure quickly enough to meet climate goals will require coordination, investment, and careful planning. Access is also uneven. Wealthier countries can afford to deploy new technologies faster. Poorer regions, often facing the worst climate impacts, may lack the resources to transition. Bridging that gap is part of the larger conversation around climate justice, ensuring that solutions are not just available, but shared fairly. Technology has always been a mirror of human priorities. It reflects what we value, what we fear, and what we hope to preserve. It can multiply problems when used without care, but it can also become part of the repair, not by replacing nature, but by aligning with it. Efficiency, circular design, renewable power, closed-loop systems, these ideas are reshaping how we think about progress. And that brings us to another part of the story. Even with all our machines and knowledge, we're not the only force acting on this planet. Sometimes the threats come from beyond, from deep space, from the sun, or from cosmic events with no warning and no preference. So we turn next to those quiet, distant hazards, the ones we rarely think about, but which have shaped Earth's past and could return again. For all the urgency we place on what's happening here on Earth, warming, pollution, habitat loss, the planet exists inside a much larger system. It's easy to forget, but space isn't empty. It's full of motion, radiation, debris, and events that operate on scales far beyond our control. Earth is a small moving target in a solar system that's active and sometimes volatile. Most of the time, space leaves us alone, but not always. Roughly 66 million years ago, a large asteroid struck what is now the Yucatan Peninsula. The impact triggered massive fires, tsunamis, and atmospheric changes that blocked sunlight for months. That single event is widely believed to have caused the extinction of most dinosaurs, along with about 3/4 of all species on Earth at the time. It was sudden, global, and irreversible, a kind of cosmic reset. Today we know more about asteroids than ever before. Thousands have been catalogued and tracked. Most are located in the asteroid belt between Mars and Jupiter, but some, known as near-Earth objects, have orbits that bring them close to our planet. NASA and other space agencies monitor these objects constantly, looking for anything large enough to cause damage if it ever crossed Earth's path. The good news is that the risk of a large impact in any given year is low. The bad news is that it's not zero. Smaller asteroids, ones that might not destroy continents but could devastate a city, are more common. The atmosphere burns up many of them before they reach the ground, but not all. In 2013, a meteor about 20 meters wide exploded over Chelyabinsk, Russia, with the force of several hundred kilotons of TNT. The shockwave injured over 1,000 people and damaged buildings across a wide area. And that was a near miss by cosmic standards. Efforts to prevent such impacts are improving. Missions like NASA's DART, which successfully altered the orbit of a small asteroid by crashing into it, show that with enough warning, it might be possible to deflect a dangerous object. But detection is key. The sooner we know something is coming, the better the chance of avoiding disaster. That's why space monitoring systems matter, even if they rarely make headlines. Asteroids aren't the only potential cosmic threat. The Sun, our life-giving star, is not entirely benign. It emits a constant stream of charged particles, the solar wind, and occasionally releases large bursts of energy called solar flares and coronal mass ejections. These events can interfere with satellites, radio communications, navigation systems, and power grids. Most are small, but large solar storms have occurred in the past. One of the most famous was the Carrington event in 1859. Telegraph systems around the world failed. Sparks flew from wires, and auroras lit up the night sky as far south as the Caribbean. If a storm of that size hit today, it could disrupt power supplies, communication networks, and internet infrastructure across continents. Some satellites could be disabled, planes might be grounded, financial systems and data centers could experience cascading failures. Space weather forecasts exist, not unlike those for terrestrial weather, but predicting solar activity is still difficult. We can see sunspots and measure flare intensity, but the timing and scale of major solar storms remain uncertain. There's ongoing work to harden infrastructure against such events, but many systems remain vulnerable. The Sun, for all its consistency, still holds the capacity for sudden change. Beyond asteroids and solar storms, there are even rarer events: gamma-ray bursts, nearby supernova, shifts in cosmic rays, that could, in theory, affect Earth's atmosphere or climate. Most of these remain speculative or distant in time and space. Their probabilities are low and their impacts depend on proximity and scale, but they serve as reminders that Earth's stability isn't entirely self-contained. There's also the ongoing issue of space debris, the fragments of satellites, rockets, and other human-made objects that now orbit Earth. As more devices are launched into space, the risk of collisions grows. These collisions can generate more debris, potentially damaging other satellites or space stations. While this doesn't directly threaten Earth's habitability, it could affect our ability to monitor and communicate, tools that are critical for managing many of the risks we face. Looking outward, some people see hope in space, a chance to explore, expand, or even escape. Space agencies and private companies are developing plans for lunar bases, Mars missions, and asteroid mining. These efforts are framed as progress, insurance, or just the next frontier. But as of now, no place beyond Earth offers the full conditions for long-term human survival. Any life off-planet would depend on artificial systems, controlled habitats, constant supply lines, and perfect engineering. A single failure in those systems would be far less forgiving than the failures we've already learned to manage on Earth. This doesn't mean space exploration shouldn't continue. Understanding other planets helps us understand our own. Satellites allow us to study weather, track deforestation, measure ice loss, and monitor pollution. Telescopes help us look further into space and time, deepening our knowledge of the universe. Missions to Mars, Venus, and the outer planets give insight into climate, geology, and the boundaries of life. But space, for all its fascination, isn't a solution to climate change, biodiversity loss, or ecosystem collapse. Earth remains the only place we know that supports complex life, not just through technology, but through naturally balanced systems of air, water, soil, and light. No amount of exploration changes the fact that we are built for this planet, shaped by it, and deeply tied to its rhythms. There's also the psychological effect of space. Astronauts often speak of the overview effect, the profound realization when seeing Earth from orbit that it is small, fragile, and deeply interconnected. No borders, no divisions, just a blue and white sphere floating in darkness. That shift in perspective has influenced science, art, philosophy, and global cooperation. Sometimes, distance reveals value. Cosmic threats may seem distant, but they put Earth into context. This planet, with its molten core, thin atmosphere, moving water, and steady orbit, is a rare and finely tuned place. The forces that made it what it is, collisions, cooling, chemical reactions, biological evolution, could easily have produced something far less hospitable, and yet here it is, stable for now. The risks from space, though real, are largely beyond our influence. What we do control is how we live within Earth's boundaries. The machines we build, the forests we cut, the energy we burn, the species we protect. These are our choices, and they shape whether this place remains safe, predictable, and supportive of the life that now depends on it. The sky can still surprise us, but so can Earth, especially if we push too far, too fast, so the story turns back downward now, into the limits we're beginning to reach, the resources that run thin, and the question of how long growth can keep going in a system with boundaries. The sun gives Earth its warmth, its light, and much of the energy that powers everything from plants to weather to cities. Every sunrise marks a fresh cycle, and every sunset draws it to a pause, a rhythm so consistent we rarely think about what the sun is, or how long it will last. But stars, like planets, have lifespans, and even the most reliable source in the sky will one day change. The sun is a middle-aged star, about 4.6 billion years old. It's powered by nuclear fusion, the process of turning hydrogen into helium in its core. That reaction releases massive amounts of energy, which pushes outward, balancing the inward pull of gravity. As long as that balance holds, the sun remains stable. Not perfectly steady, it has cycles and flares, but generally reliable. Eventually, though, it will run out of fuel. Not soon. The sun has about 5 billion years left before its core exhausts the hydrogen it needs to keep burning in the way it does now. But when that shift begins, the changes will be gradual at first, and then more dramatic. It will expand, grow brighter, and become unstable. Not in a sudden flash, but in stages. Even now, the sun is slowly getting brighter. Astronomers estimate that over the past few 100 million years, solar luminosity has increased by about 10%. Over the next billion years, that trend will continue. Earth's temperature will slowly rise even without any help from greenhouse gases. Eventually the oceans will begin to evaporate, water vapour will increase, and the planet's climate will shift in ways that no living thing today could survive. This isn't a problem for humans in the way climate changes. It's not something we can affect, and it won't happen in a timescale that overlaps with any current plan or crisis. But it's still worth understanding because it puts Earth into a longer story, one where even the most stable systems have endpoints. As the Sun gets older, its core will contract and its outer layers will expand. It will become a red giant growing large enough to potentially engulf Mercury and Venus. Whether Earth gets swallowed is uncertain. Some models suggest it might be spared, but not by much. Even if the planet remains outside the Sun's surface, the conditions will be unrecognisable. The atmosphere stripped, the surface scorched, the crust possibly melted. By that time, life on Earth will be long gone, unless it's taken to space or transformed in ways we can't yet imagine. The biosphere depends on a narrow range of conditions: temperature, pressure, chemistry, and those will fall out of balance as the Sun evolves. After the red giant phase, the Sun will shed its outer layers and become a white dwarf, a dense hot remnant about the size of Earth, but with half the Sun's mass. It won't produce energy through fusion anymore. It will simply cool, slowly over trillions of years, eventually fading into darkness. But by then, Earth, if it still exists, will be a quiet, frozen rock orbiting a faint light. None of this is unique to our solar system. It's the standard life cycle for stars of the Sun's size. Larger stars burn faster and die more violently, the supernova explosions that scatter heavy elements into space. Those explosions, in fact, are how many of the elements in your body were formed. The calcium in your bones, the iron in your blood, the carbon in your cells, forged in earlier stars long before Earth existed. This long perspective shifts how we think about habitability. Earth is not permanently safe. It has been through mass extinctions, deep freezes, volcanic winters, asteroid strikes and climate swings. It will eventually face an end far beyond anything driven by human activity. But that doesn't make today's challenges less urgent. It just adds another layer of context, a reminder that even without us, the clock is always ticking. Knowing this also reshapes how we think about other planets. Mars, for example, once had liquid water. Venus may have had a more temperate climate before its atmosphere thickened. As the Sun brightened, these planets crossed key thresholds, losing the conditions that could support life. Earth sits in a narrow window, a zone of balance that won't last forever. There's also the question of what happens to everything humans have built. Even if we disappear, our satellites, probes, rovers and stations might drift on for a while. Silent pieces of machinery slowly breaking down in the cold of space or the heat of re-entry. Earth's surface would eventually erode most signs of civilization. Forests, oceans and weather would reclaim concrete and steel, though how fast depends on how those systems survive. If some form of life adapts or evolves to survive the next few 100 million years, it will face the long brightening of the Sun as a final boundary. Unless it finds a way off Earth, or a way to control or move the planet, ideas that belong more to science fiction than science at the moment, that life will face an unlivable future no matter how advanced it becomes. Still, the vastness of time makes some questions harder to hold. 1 billion years is not something the human brain is designed to picture. What matters more immediately is what happens over the next few decades, the part of the story we still influence. If anything, the Sun's eventual death highlights how temporary even the most permanent things can be. That doesn't make effort meaningless. It makes it more meaningful. We live in a brief moment when Earth is habitable, when the atmosphere is stable, and when humans are capable of understanding both our limits and our reach. This moment won't last forever, but it's ours now. And with that sense of scale, we return to the present, to the choices we still make each day, the systems we depend on, and the limits that come not from the stars, but from the resources we draw from a finite world. We tend to think of Earth as solid, fixed and stable, spinning in place, tilted just right, moving predictably around the sun. For most daily purposes, that's true. The ground stays still beneath our feet, the seasons follow a familiar cycle, and the length of the day remains more or less constant. But over longer timescales, Earth doesn't sit quite so still. It shifts, tilts, and wobbles, slowly, silently, and with real consequences. These changes are known as Milankovitch cycles, after the Serbian scientist Milutin Milankovic, who studied how variations in Earth's orbit and rotation influence climate over thousands of years. There are three main cycles: eccentricity, obliquity, and precession. Each one alters how much sunlight reaches different parts of the planet and how that energy is distributed across seasons and latitudes. Eccentricity refers to the shape of Earth's orbit around the Sun. It's not a perfect circle, but a slightly stretched ellipse. Over a cycle of about 100,000 years, the orbit becomes more or less elliptical. When the orbit is more circular, Earth stays roughly the same distance from the Sun all year. When it's more elliptical, the distance varies more between seasons. This affects the intensity of seasons, especially in the hemispheres. Obliquity is the tilt of Earth's axis, the angle between the planet's rotational axis and its orbital plane. Right now that tilt is about 23.5 degrees. It's the reason we have seasons at all. As Earth orbits the Sun, different hemispheres tilt toward or away, creating variations in sunlight. But that tilt isn't fixed. It wobbles between about 22 and 24.5 degrees over a 41,000-year cycle. When the tilt is higher, seasons become more extreme. When it's lower, seasons are milder. Precession is the slow wobble of Earth's axis, similar to the motion of a spinning top. This cycle takes about 26,000 years. It gradually shifts the orientation of Earth's axis relative to its orbit, changing the timing of the seasons. Over time, this means that the northern hemisphere's summer could occur when Earth is farthest from the Sun instead of closest, altering the strength and timing of seasonal differences. These cycles don't act alone. They combine in complex ways, and their influence isn't immediate. They shift the distribution of solar energy slowly, which then interacts with ocean currents, ice sheets, greenhouse gases, and vegetation. The effects can take thousands of years to unfold, but when they do, they can help trigger major changes, including the advance and retreat of ice ages. No, for the past few million years, Earth has experienced a pattern of glacial and interglacial periods, roughly every 100,000 years. Ice sheets expanded across North America, Europe, and Asia, then melted back. Sea levels dropped and rose. Ecosystems migrated and reformed. These shifts were driven partly by Milankovitch cycles, amplified by feedbacks like albedo, the reflectivity of ice and snow, and the concentration of carbon dioxide in the atmosphere. We are currently in an interglacial period, known as the Holocene, which began around 11,700 years ago. It's been unusually stable, enough to support the rise of agriculture, cities, and modern civilization. If left to natural cycles, Earth would likely remain in a warm phase for another several thousand years before beginning a slow descent into another ice age. But human emissions have altered that trajectory. The levels of carbon dioxide and other greenhouse gases in the atmosphere now exceed anything seen during past interglacials. That means the natural rhythm of climate, the slow dance of wobbles and tilts, is being overridden by much faster changes. The climate is warming far more rapidly than it ever has under orbital changes alone. Even if a cooling phase were due, greenhouse gases have pushed the system in the opposite direction. Still, the underlying cycles continue. Earth's orbit continues to shift. The axial tilt continues to change. Precession continues to nudge the calendar of seasons. These changes may become more relevant again over longer timescales, tens of thousands of years. But right now, the dominant force on climate is not orbital mechanics. It's human activity. These cycles are also not the only way Earth moves. The axis itself shifts slightly from year to year due to changes in the distribution of mass on the planet. Melting ice, groundwater depletion, and even large-scale movements of air and water can alter the spin. These shifts are tiny, often measured in milliseconds, but they're detectable with modern instruments. Over time, they can affect the length of the day by milliseconds. There's also a phenomenon called true polar wander, which involves a reorientation of the entire solid Earth relative to its rotational axis. It's different from precession and much slower, but it shows that even the large-scale structure of the planet is not entirely fixed. Geological records suggest that true polar wander has occurred in the past, likely linked to changes in Earth's internal dynamics. These subtle shifts have practical effects. Satellite positioning, GPS systems, and astronomical calculations all depend on knowing Earth's exact orientation. Even climate models factor in orbital parameters to understand past and future conditions. The better we understand these slow movements, the better we can separate natural trends from human-driven ones. What all of this reveals is that Earth's habitability has always depended on a delicate balance, not just in atmospheric chemistry, but in the way sunlight is delivered to the surface. Small shifts, when amplified by feedbacks, can lead to major changes. Ice sheets don't respond instantly, but once they begin to grow or melt, the momentum can carry through millennia. These cycles also highlight that Earth's climate has always changed. What's different now is the pace. Natural changes unfold over thousands to millions of years. The current warming is happening over decades. That difference in speed is critical because ecosystems, agriculture, and infrastructure are built around stability. When conditions change faster than systems can adapt, the risk of disruption increases. It's also important to remember that while we can't control Earth's orbital variations, we can choose how we respond to the changes happening now. The tilt of the axis, the shape of the orbit. These aren't things we can influence. But emissions, land use, energy choices, those are within reach. Some people look to these cycles as a way to downplay human influence on climate, arguing that warming might be natural. But the data doesn't support that. Climate models that include only orbital changes don't explain recent trends. Only when greenhouse gases are included do the patterns match the observations. The natural rhythms are still there, but they are being drowned out by a stronger signal. So Earth continues to spin, slowly wobbling on its axis, orbiting a star that is itself evolving. The cycles continue, shaping long-term patterns in ways that used to be dominant but are now part of a larger picture, one where human choices have become the most immediate source of planetary change. The motion of the planet is subtle, slow, and almost invisible from day to day. But over time, it adds up, and just like the movement of water, air, and ice, it reminds us that even things that feel stable are always in motion. Ice might seem like the opposite of life, cold, still, and silent, but in many ways it's one of the most informative materials on Earth. Locked inside glaciers and ice sheets are records of past climates, ancient air, shifting temperatures, and the long, slow memory of the planet. When scientists want to understand how Earth's systems behaved before satellites, thermometers, or written history, they often turn to ice. Glaciers form where snowfall accumulates year after year, compacting under its own weight into dense crystalline layers. Over time, that layered ice flows slowly downhill, shaped by gravity and topography. In some places, like Greenland and Antarctica, these flows stretch across entire continents, forming ice sheets that are kilometers thick. Each layer captures traces of the atmosphere at the time it formed. Tiny air bubbles, dust, volcanic ash, pollen, and isotopes of oxygen and hydrogen that reflect temperature conditions. By drilling deep into these layers, scientists can reconstruct climate records stretching back hundreds of thousands of years. The oldest ice cores provide snapshots of Earth's atmosphere going back more than 800,000 years. They show a repeating pattern, glacial periods, where ice sheets expanded and sea levels dropped, followed by warmer interglacials like the one we're in now. These shifts were often gradual, tied to orbital changes and reinforced by feedbacks. One of the clearest signals in the ice is the connection between carbon dioxide and temperature. During glacial periods, CO2 levels were low. During warm periods, they rose. The cause and effect work both ways. Warming releases carbon, and carbon drives more warming. It's a feedback loop, not a straight line. But the pattern is consistent. When CO2 rises quickly, temperatures follow. The ice also shows that current carbon dioxide levels are far outside the natural range for the last several 100,000 years. Since the Industrial Revolution, atmospheric CO2 has increased more than 50%, reaching levels not seen in at least 3 million years. The rate of increase is faster than anything found in the ice core records. That speed matters because it gives natural systems less time to adjust. As the planet warms, glaciers and ice sheets respond. Mountain glaciers around the world are retreating, from the Alps to the Andes, from Alaska to the Himalayas. In many cases, the change is visible within a single human lifetime. Some smaller glaciers have already disappeared completely. These losses affect more than just scenery. Glaciers store water that supports agriculture, drinking supplies, and river systems downstream. When they shrink, seasonal water flows change. At the poles, the story is larger in scale. Greenland's ice sheet holds enough water to raise sea levels by about 7 meters if fully melted. Antarctica contains much more, enough to raise sea levels by over 50 meters. Those outcomes are not expected in the near future, but the direction of change is already underway. Both ice sheets are losing mass. Some parts are thinning, others are accelerating as the ice slides more quickly toward the sea. What drives this isn't just surface melt. In many places, warm ocean water is flowing beneath ice shelves, the floating extensions of glaciers that help hold back the flow. When these ice shelves thin or collapse, the glaciers behind them speed up. That's happening in West Antarctica and parts of Greenland. The process is uneven, but once it begins, it can be difficult to stop. Some ice systems may already be on paths toward long-term retreat, even if warming slows. These processes also involve feedback loops. As ice melts, it exposes darker land or water underneath. These surfaces absorb more sunlight than ice, which accelerates local warming. That's the albedo effect, another reinforcing cycle. In the Arctic, this has led to especially rapid changes. Summer sea ice has declined dramatically over the past few decades. Less ice means more heat absorption, which leads to less ice the following year. Permafrost, frozen soil in polar regions, holds vast amounts of carbon in the form of decayed plant material that never fully decomposed. As the ground thaws, microbes become active and begin breaking down that organic matter, releasing carbon dioxide and methane into the atmosphere. Methane is particularly potent as a greenhouse gas. This process is slow and patchy, but it adds yet another feedback loop to the climate system. Ice doesn't just reflect changes, it amplifies them, but it also records them. Ice cores have revealed evidence of past volcanic eruptions, massive wildfires, and shifts in atmospheric composition. They've helped confirm that recent warming is unusual in both pace and scale. They serve as long-term context for current changes, not as predictions, but as comparisons. They remind us that while Earth's climate has always varied, it usually did so over thousands of years, not decades. There are limits to what ice can reveal. The cores are limited to places where long-standing glaciers exist. Most data comes from Antarctica and Greenland, with smaller records from high mountain ranges. Tropical regions, oceans, and deserts don't preserve ice. Other proxies, like tree rings, sediment layers, and coral growth, help fill the gaps. But for understanding deep time and ancient air, ice remains unmatched. Loss of ice also brings physical consequences. As glaciers and ice sheets melt, sea levels rise. So far, most sea level rise has come from the thermal expansion of warming water, but increasingly melting ice is becoming the dominant factor. Sea level rise is not uniform. It varies based on ocean currents, gravitational changes, and local land movement. But the trend is consistent. Global averages are rising, and the pace is accelerating. This affects coastal cities, island nations, estuaries, and wetlands. Saltwater intrusion affects groundwater. Flooding becomes more frequent. Infrastructure designed for 20th century conditions struggles to keep up. Adaptation is possible through seawalls, zoning changes, and wetland restoration, but it takes planning, resources, and long-term thinking. The ice story also intersects with geopolitics. As Arctic sea ice retreats, new shipping routes open. Oil and gas reserves become more accessible. Countries are investing in Arctic military bases, ports, and research stations. This creates new tensions in a region that was once largely inaccessible. It's another way in which climate change affects not just ecosystems, but the strategic interests of nations. For indigenous communities in polar regions, ice loss is more than an environmental concern. It's a disruption of culture, tradition, and livelihood. Hunting patterns change. Travel becomes dangerous. Sacred places disappear. The knowledge systems that evolved in partnership with ice are being tested in new ways. Many communities are adapting, combining traditional knowledge with modern tools. But the pace of change is rapid. Even in places far from glaciers, ice loss has ripple effects. Changes in Arctic sea ice affect jet streams and weather patterns across the northern hemisphere. Some researchers link reduced ice cover to more persistent weather systems. Longer heat waves, stalled storms, colder winters in some areas. These connections are still being studied, but the links between polar changes and global patterns are growing clearer. There's still time to avoid the worst outcomes. Ice sheets don't melt overnight. With aggressive emissions reductions and smart adaptation, some retreat could be slowed or stabilised. Feedback loops can be softened. But they can't be reversed once certain thresholds are crossed. That's why ice is often seen as a warning system. Slow to change at first, but hard to stop once moving. So ice is not just frozen water. It's a climate archive, a feedback mechanism, a geographic force, and a signal. When it moves, it signals that the planet's systems are shifting. When it melts, it marks a turning point. And when it disappears, it takes with it not only mass, but memory. Cities are often seen as symbols of progress, places where technology, culture, economy, and infrastructure come together. They're dense, active, and filled with systems built to support modern life. But they also reveal how human activity concentrates energy, heat, and impact in ways that ripple outward. In a world facing rising temperatures and shifting climates, cities are becoming both more important and more vulnerable. Over half of the world's population now lives in urban areas. That number is expected to grow, especially in Asia and Africa, where cities are expanding rapidly. Urbanization brings opportunities, access to services, jobs, education, healthcare, but it also creates pressure. Land is paved, trees are removed, buildings rise, vehicles crowd the streets. Each piece adds to the overall load on the environment. One of the clearest effects is the urban heat island phenomenon. Cities tend to be warmer than surrounding rural areas, often by several degrees, especially at night. The reason is simple. Dark surfaces like asphalt and concrete absorb heat during the day and release it slowly at night. In rural areas, vegetation helps cool the air through evaporation and shading. In cities, those cooling systems are often missing or diminished. This extra heat has real effects. It increases demand for air conditioning, which adds stress to power grids and can increase emissions unless powered by clean energy. It raises the risk of heat-related illnesses, especially for vulnerable populations, the elderly, outdoor workers, and people without access to cooling. In extreme cases, heat waves in cities can lead to spikes in mortality. Urban heat isn't evenly distributed. Wealthier neighbourhoods often have more trees, better insulation, and access to cooling. Poorer areas may have fewer green spaces, older infrastructure, and less support during heat emergencies. This creates a form of environmental inequality, where the risks of climate change are amplified by local conditions. City design can either soften or worsen these effects. Materials matter. Lighter coloured surfaces reflect more sunlight. Vegetation helps cool the air and manage stormwater. Green roofs, tree canopies and parks reduce temperature spikes. Water features add humidity and cooling potential. Transit systems reduce reliance on cars, lowering heat from engines and tailpipes. Every design choice adds up. Noise is another feature of urban life that often goes unnoticed. Cities are filled with sounds. Engines, sirens, construction, voices, machines. Over time, constant noise can affect sleep, stress levels, cardiovascular health, and mental well-being. It also affects wildlife. Birds, for example, may alter their calls in noisy areas or avoid them entirely. Insects, mammals, and even aquatic species in urban waterways are influenced by human soundscapes. Light is the third layer, bright, constant and growing. From office towers to street lamps to billboards, cities shine all night. This light makes streets safer and activity possible after dark. But it also interferes with natural rhythms. Human bodies respond to light cues to regulate sleep, hormones, and alertness. Constant exposure to artificial light at night can disrupt those patterns, leading to fatigue, metabolic issues, and reduced sleep quality. Wildlife responds too. Many animals rely on darkness to feed, migrate, or reproduce. Artificial light can disorient birds, turtles, insects, and other species. It changes predator-prey dynamics, alters reproductive timing, and fragments habitats. Even plants exposed to prolonged lighting may shift their growth cycles. Over time, the night becomes less of a boundary and more of a diluted version of the day. There are ways to reduce light pollution. Shielded fixtures, warmer colour temperatures, dimming schedules, and thoughtful placement all help. Some cities are beginning to adjust their lighting strategies for both human health and ecosystem protection. But in many places, the night sky remains washed out, a few stars visible where thousands should be. The environmental footprint of cities extends beyond their boundaries. They depend on resources gathered elsewhere. Food from rural areas, water from distant sources, energy from regional grids, materials from global supply chains. Waste produced in cities often ends up exported in landfills, oceans, or incinerators, affecting communities far from where it originated. Urban centres also produce a large share of global emissions. Buildings require heating and cooling. Cars and trucks burn fuel. Industry and infrastructure consume power, but cities also concentrate solutions. Transit systems, dense housing, energy-efficient buildings and shared resources all offer ways to reduce per-person impact. When planned well, urban living can actually be more sustainable than suburban sprawl or dispersed development. Adapting cities to a changing climate means addressing multiple risks at once. Not just heat, but also flooding, storm surges, drought, air quality, and social vulnerability. It means upgrading infrastructure that was built for a different climate. Pipes, bridges, roads, electrical systems. And it means doing so while housing growing populations, supporting economies, and maintaining services. Some cities are already taking action. Urban planners are integrating green infrastructure, bioswales, rain gardens, permeable pavement to manage stormwater and reduce flooding. Others are building cooling centres, planting urban forests, and revising building codes for energy efficiency. Some are investing in resilient transit, renewable energy, and microgrids that can operate independently during outages. Community involvement is key. Climate adaptation isn't just a technical challenge, it's social. Residents know their neighbourhoods. They understand local needs and histories. Including them in planning leads to better outcomes, more trust, and more equitable solutions. Grassroots efforts, from community gardens to cooling campaigns, often move faster than top-down programs. Technology plays a role as well. Sensors measure temperature, air quality, and noise in real time. Data helps target interventions where they're needed most. Digital tools can support smart grid management, real-time transit updates, and citizen reporting of problems. But technology is a tool, not a solution on its own. It works best when combined with strong governance, good design, and public engagement. Not all cities have equal resources. Wealthier places can invest in adaptation. Poorer cities may struggle with basic infrastructure, even before climate stress is added. International support, knowledge sharing, and flexible financing models are needed to close those gaps. Climate resilience shouldn't be a luxury. It should be a standard. Cities also shape culture, behaviour, and norms. The way people move, eat, cool their homes, and interact with nature is influenced by the urban environment. That makes cities powerful places for change. If cycling is safe, more people will do it. If buildings are efficient, energy use falls. If neighbourhoods are green, heat stress drops. And if the sky is dark enough, people might look up again. Urban areas are not separate from nature, they are part of it. They sit on land that was once forest, prairie, or wetland. Rain still falls, rivers still flow, wildlife still passes through. Recognising that connection and designing with it makes cities not just more livable, but more resilient. The challenge ahead is not whether cities will change, but how. Will they expand with more asphalt, more emissions, and more fragmentation? Or will they grow in ways that reflect limits, adapt to risks, and create new forms of balance? We don't often think about air. It's invisible, weightless in our perception, and always around us. So constant that it blends into the background of daily life. We notice it when it's fresh, or when something smells odd, or when it's hard to catch a breath. But for the most part, air just works. It comes in with a breath, delivers oxygen, carries away carbon dioxide and keeps our cells supplied. Without it, life stops. Not in years or hours, but in minutes. Air seems so abundant that it feels permanent, but it isn't. Like water, soil and temperature, air quality and composition are subject to change. Not just on short timescales, with wildfires, dust storms or pollution events, but over long arcs, when the chemistry of the atmosphere begins to shift. Some changes are local, others global. Some are reversible, others less so. And some pose the question directly: could air, the very thing we rely on most, become unbreathable? The atmosphere is a thin shell, about 100 kilometres from the surface to the edge of space, though most of the breathable air is in the lowest 10 kilometres, the troposphere. It's made mostly of nitrogen, 78%, and oxygen, 21%, with small amounts of argon, carbon dioxide, water vapour, and trace gases. That mix has stayed fairly stable during the period when complex life evolved, stable enough to support lungs, gills, leaves, and ecosystems of all kinds. Oxygen is the key to animal life. Too little, and cells can't function. Too much, and it becomes toxic, damaging tissues and increasing fire risk. Earth's atmosphere didn't always have this balance. In its early history, oxygen was nearly absent. It took billions of years, and the rise of photosynthetic microbes, to raise levels to something breathable. That process, known as the Great Oxidation Event, was slow, chaotic, and transformative. It allowed for the emergence of complex organisms, but also caused one of the planet's earliest mass extinctions, killing off many species that couldn't tolerate the new chemistry. Today, oxygen levels are relatively stable, but they're not guaranteed. If carbon emissions continue to drive warming and ocean oxygen loss, there's a potential, still distant, that atmospheric oxygen could decline slightly over centuries or millennia. Not to levels that make breathing impossible, but enough to affect health, agriculture, and fire dynamics. It's not a primary risk, but it's a reminder that even stable components can shift under long-term pressure. What's more immediate is air pollution. Across much of the world, especially in urban and industrial areas, air can become hazardous to health. Pollutants include particulate matter, PM2.5 and PM10, nitrogen dioxide, sulfur dioxide, ground-level ozone, and volatile organic compounds. These come from vehicles, factories, power plants, burning biomass, and construction. When inhaled, they can enter the lungs, the bloodstream, and even the brain. Air pollution contributes to millions of premature deaths each year. It increases the risk of heart disease, respiratory conditions, stroke, and certain cancers. Children, the elderly, and those with pre-existing conditions are especially vulnerable. Short-term exposure can trigger asthma attacks or fatigue. Long-term exposure reduces life expectancy and impairs cognitive development. In some regions, air quality is so poor that people wear masks daily, even before the global pandemic made them common. Pollution is not evenly distributed. Lower-income communities and marginalised groups often live closer to industrial zones, highways, and polluting facilities. This creates a double burden: social inequality paired with environmental stress. Efforts to improve air quality through cleaner energy, vehicle regulations, and public transit often bring multiple benefits, but they require political will, investment, and enforcement. Wildfires have become another source of unbreathable air. As forests dry out and burn more frequently, smoke can travel hundreds or thousands of kilometres, blanketing regions in haze. The fine particles in wildfire smoke are especially dangerous, able to penetrate deep into the lungs and cross into the bloodstream. These events are episodic, but increasingly common in areas like California, Australia, and southern Europe. Ground-level ozone, formed when sunlight interacts with pollutants like nitrogen oxides and volatile organics, is another concern. It's not the ozone high in the stratosphere that protects against UV radiation, but a harmful form that irritates airways and reduces lung function. Ozone levels tend to spike in hot weather, making heat waves and pollution worse when combined. In some parts of the world, sand and dust storms add to the mix. The soils dry out and vegetation cover shrinks. Wind lifts fine particles into the air. These events are common in desert regions, but land degradation and climate change are expanding their reach. Dust can affect respiratory health, block sunlight, and carry bacteria or fungi long distances. Then there's indoor air. People spend a large portion of their time inside, at home, work, or in transit. Indoor air quality is affected by cooking, cleaning products, building materials, and ventilation. In poorly ventilated spaces, pollutants can build up, especially in energy-efficient buildings that are tightly sealed. Mold, radon, carbon monoxide, and chemical fumes are common indoor concerns. Solutions include better filters, fresh air systems, and careful material choices, but awareness is often low. There's also the question of altitude. At high elevations, air pressure drops and oxygen becomes thinner. Human bodies can adapt to a point, but above about 8,000 meters, the death zone, even acclimatized climbers can't survive for long without supplemental oxygen. That's a reminder that breathable air depends not just on chemistry, but also pressure and delivery. If Earth's climate or atmospheric pressure were to change dramatically, the capacity to breathe would not be a given. Geoengineering proposals, such as solar radiation management or carbon capture, could also, if done carelessly, alter atmospheric chemistry. Most models are designed to avoid harmful side effects, but uncertainties remain. Any large-scale intervention in Earth systems carries the risk of unintended consequences. Air is not just a place to dump gases. It's part of a finely tuned system that touches every breath and every ecosystem. Yet, there are hopeful signs. Air quality has improved in many places where regulations have been enforced. The Clean Air Act in the United States, for example, has led to sharp reductions in key pollutants over the past few decades. Europe, Japan, and parts of China have made progress as well. Even short-term lockdowns during the COVID-19 pandemic revealed how quickly skies can clear when emissions drop. Sensors are becoming more affordable and widespread. Citizen science projects now allow people to measure local air quality and share data in real time. Satellite monitoring provides a global view of pollution trends, These tools improve transparency, guide policy, and help people protect themselves during high-risk days. Transitioning to cleaner energy, reducing fossil fuel use, electrifying transport, and investing in green infrastructure all contribute to better air. Trees and plants also help, filtering particles, producing oxygen, and moderating temperatures. Urban planning that prioritizes walking, cycling, and public transit reduces tailpipe emissions and spreads benefits across communities. The question of unbreathable air isn't just about worst-case scenarios, it's about cumulative exposure, unequal risk, and long-term health. Most people won't face a day when oxygen vanishes, but many already live with air that slowly wears them down. And in that sense, the atmosphere is changing in ways that are both subtle and significant. Air is not just chemistry, it's context. It carries pollen, spores, bacteria, and moisture. It links ecosystems. It moves seeds and signals. It cools the skin, fills the lungs, carries voices. It's the medium in which all land life exists. And when that medium is compromised, the effects are widespread, not just on individuals, but on entire systems. Life is persistent. It has found ways to adapt to boiling sulfur springs, frozen deserts, deep ocean trenches, and radioactive waste. There are microbes that survive in acid, algae that live inside rocks, and animals that go dormant for years. These forms of life don't just tolerate extreme conditions, they thrive in them. And by studying those edge cases, scientists gain insight into the flexibility and limits of biology. The biosphere, the zone of life on Earth, stretches from the deepest microbes in oceanic crust to high-altitude bacteria floating in the upper atmosphere. But most complex life exists in a much narrower band, within a few kilometers of elevation and a relatively small range of temperatures, pressures, and chemical compositions. That band isn't fixed, and organisms can shift within it, but the edges tell us where the boundary lies between survivable and not. In the high Andes and Himalayas, people live at elevations where oxygen is scarce and temperatures are low. These populations have developed unique physiological adaptations, increased lung capacity, higher red blood cell counts, and altered metabolism. Yet there's still a ceiling. Above a certain point, human life without assistance becomes impossible. The air thins, temperatures drop, UV radiation increases. Eventually, even the most adapted bodies can't function. In the deep ocean, some organisms survive under immense pressure, in complete darkness, using chemosynthesis instead of photosynthesis. Around hydrothermal vents, bacteria convert sulfur compounds into energy. Tube worms, clams, and other animals cluster around these vents, forming isolated ecosystems. But they depend on the vent's heat and chemistry. When a vent dies, the life around it fades. These are not generalist systems, they are tuned to narrow conditions. Deserts test life in the opposite way, through dryness. Some microbes survive in Atacama soils where it may not rain for years. They draw moisture from the air or use metabolic water. Desert plants slow their growth, store water, and protect their tissues from sun. Animals burrow, migrate, or adapt their behavior to minimize heat and water loss. But even here, there's a limit. Past a certain threshold of aridity and heat, life gives way to sterility. Polar regions add cold to the mix. In Antarctica, simple organisms survive in ice-covered lakes, in cracks within rocks, or in seasonal melt zones. Algae bloom in sea ice. Penguins and seals thrive along the coasts. But deeper into the interior, where cold is relentless and resources are scarce, biological activity drops to near zero. The ice becomes more mineral than ecosystem. These edge zones matter because they show what life can do, and what it can't. As Earth warms, dries, and shifts, some areas may become more like these extreme environments. Coastal zones could flood. Inland areas could overheat. Forests could transition to grasslands, then to scrub, then to dust. The biosphere can move, but only so far. Species can adapt, but only so fast. Some organisms respond by migrating. Plants shift their ranges uphill or poleward, birds alter their routes, fish change spawning grounds, but migration assumes there's somewhere to go, that suitable habitat exists and is accessible. In fragmented landscapes, that's not always true. Roads, cities, and agriculture can block movement. Climate zones may shift faster than species can track them. Others adapt in place. Some plants flower earlier. Some insects adjust their life cycles. Coral reefs, under stress, may host more heat-tolerant algae. But adaptation has costs. Energy spent on tolerance is energy not spent on growth or reproduction. Over time, if stress continues, populations decline, and many species, especially those with long generation times or specialized niches, may not adapt at all. Extinction is the end point of this pressure. It's a natural process, but current rates are much higher than background levels. Habitat loss, pollution, climate change, invasive species, and overexploitation all play a role. Some estimates suggest that 1 million species are at risk of extinction in the coming decades. That includes not just obscure insects or rare plants, but larger animals, keystone species, and systems on which others depend. Biodiversity isn't just about numbers, it's about function. Diverse systems tend to be more resilient, better at absorbing shocks, recovering from damage, and supporting complex interactions. When species disappear, those interactions weaken. Pollination, seed dispersal, soil formation, water filtration, all rely on networks of organisms. When those networks fray, ecosystems become more brittle. Microbial life, the foundation of many systems, is also sensitive to environmental change. In soil, microbes cycle nutrients, decompose organic matter, and support plant roots. In oceans, plankton form the base of the food web and help regulate carbon. Shifts in temperature, acidity, and chemistry can disrupt these roles. Ocean acidification, driven by excess carbon dioxide, is already affecting shell-forming organisms like corals and mollusks. That disruption echoes upward through the food chain. Some researchers are exploring ways to engineer resilience through assisted migration, selective breeding, or even genetic modification. These tools are controversial and uncertain. Moving a species to a new habitat might solve one problem but create another. Altering genes raises questions of unintended consequences. But the fact that such strategies are even considered reflects how serious the situation has become. There's also interest in synthetic biology, designing organisms that can survive in harsh conditions, remove pollutants, or capture carbon. These ideas are in early stages. They offer promise, but also risk. Ecosystems are not simple machines. Inserting a new part may not lead to predictable results. At the same time, traditional knowledge systems offer insights into adaptation. Indigenous communities often understand how species respond to subtle changes. They track seasonal shifts, monitor animal behaviour, and adjust practices based on observation. These forms of knowledge are rooted in place and time. They provide context that complements scientific models and can guide more grounded, localized responses. On a planetary level, the biosphere is not in full collapse. Many systems still function. Forests still breathe in carbon, wetlands still filter water, grasslands still feed grazers, but pressure is rising, and the limits of adaptation are becoming clearer. When we look at Mars or Venus, we see worlds without life, either too cold or too hot, too dry or too acidic. Earth is different not because life appeared here, but because life co-evolved with the planet to shape and regulate its systems. That balance was not accidental. It was built over billions of years. It's robust in some ways, fragile in others, and when it's pushed too far, it can change in ways that no longer support the kinds of life we recognize. The edges of the biosphere aren't just remote or exotic. They're moving closer, appearing in cities, in coasts, in forests that burn or don't grow back. What was once rare becomes common. What was once marginal becomes central. And that leads to new questions about how much life can adapt, how much can be helped, and how much may be lost. When people talk about climate change or environmental collapse, the conversation often swings between extremes: despair and denial, panic and paralysis. The scale of the problem is large. The systems involved are complex. The timeline feels both urgent and abstract. But somewhere between fear and fantasy is a space for practical, ongoing work, not to reverse every change, but to slow the damage, soften the impact, and protect what still functions. That space is where mitigation and adaptation live. Mitigation means reducing the causes of environmental change, mostly by cutting greenhouse gas emissions. Adaptation means adjusting to the changes already underway, through better planning, infrastructure, and resilient strategies. Both are necessary. Neither is a full solution on its own. Mitigation often starts with energy. Fossil fuels, coal, oil, and natural gas are the main source of carbon dioxide emissions. Shifting away from them means expanding clean energy: solar, wind, hydro, geothermal, and in some cases nuclear. Each has trade-offs, but all avoid the carbon load of burning hydrocarbons. The costs of renewables have dropped dramatically in recent years. In many places they are now the cheapest form of new electricity. But replacing the global energy system takes time and coordination. It involves not just generation, but storage, transmission, and regulation. Solar panels only work during the day. Wind isn't constant. That means grids must be flexible. Batteries, pumped storage, and smart distribution networks all help balance supply and demand. These aren't futuristic ideas. They're already in use in places like California, Germany, and parts of China. Transportation is another key sector. Cars, trucks, ships, and planes burn fossil fuels. Electrifying vehicles, improving public transit, and redesigning cities to support walking and cycling all reduce emissions. Aviation is hard to decarbonise, but alternative fuels and efficiency improvements are in development. Shipping can shift to cleaner fuels and smarter logistics. Every percentage point matters. Buildings also matter. Heating, cooling, lighting, and appliances all consume energy. Retrofitting old buildings for efficiency, better insulation, efficient systems, smart controls, saves both money and emissions. New buildings can be designed to be passive, using sunlight, shading, and airflow to maintain comfort with minimal energy use. Urban planning shapes these outcomes too. Denser cities with mixed-use zoning reduce travel needs and support shared systems. Industry, especially cement, steel, and chemicals, produces a large share of emissions. Some of this is hard to replace. High temperatures and specific chemical reactions are difficult to replicate without carbon. But innovation is moving fast. Carbon capture, alternative materials, and circular design all play a role. Some factories are experimenting with hydrogen, electric kilns, or carbon-negative production processes. Agriculture contributes through land use, methane, and nitrous oxide. Livestock, rice paddies, and fertilizer all release potent greenhouse gases. Reducing meat consumption, improving feed, managing manure, and adopting regenerative practices can lower the footprint. Precision agriculture, using data to apply water, nutrients, and treatments only where needed, increases efficiency. Shifting subsidies towards sustainable practices aligns incentives. Forests, wetlands, and soils act as carbon sinks. Protecting and restoring these systems helps draw down CO2. But it's not just about planting trees. Diverse, native ecosystems store more carbon and support more biodiversity than monoculture plantations. Wetlands filter water, buffer floods, and capture methane. Soil health affects both productivity and carbon storage. Land use planning must consider not just how much is covered in green, but what kind of green and where. There's also interest in carbon removal. Technologies or strategies that take CO2 out of the air. These include direct air capture, bioenergy with carbon capture, enhanced weathering, and ocean fertilization. Most are in early stages and require energy and materials. They are not replacements for emissions reductions, but potential supplements. The risks, costs, and scalability are still being studied. On the adaptation side, the work is just as varied. Coastal defences, seawalls, dunes, mangroves reduce flood risk. Early warning systems help communities prepare for storms, droughts, or heat waves. Insurance models are evolving to reflect new risks. Building codes are being updated. Infrastructure is being moved or redesigned. Some cities are restoring natural buffers, letting rivers flood into designated areas or reconnecting wetlands to absorb runoff. Water management is a growing focus. Droughts, floods, and shifting rainfall patterns affect agriculture, drinking supplies, and ecosystems. Efficient irrigation, groundwater recharge, rainwater harvesting, and wastewater reuse all help balance supply and demand. In some regions, cooperation across borders will be necessary, as rivers flow through multiple countries and decisions upstream affect users downstream. Adaptation also includes social systems. Health services must respond to heat stress, disease shifts, and mental strain. Education systems can prepare students for green jobs. Emergency response must account for compound disasters, wildfires followed by floods, storms during pandemics, supply chain disruptions. Equity is central. Vulnerable communities often face the greatest risks and have the fewest resources to cope. Technology plays a role, but it's not a cure-all. Apps can track air quality, warn of fires, or guide energy use. Sensors monitor crops, power grids, and flood zones. AI helps model climate risks and optimize systems. But without good policy and inclusive governance, tools can become distractions or deepen inequality. What matters is how they are used and who they serve. Finance is another lever. Investments shape the future. Banks, insurers, and asset managers are beginning to factor climate risk into decisions. Some countries are shifting subsidies away from fossil fuels. Green bonds, climate funds, and carbon pricing are tools to align markets with sustainability. These mechanisms are imperfect, but they signal a shift in how risk and value are understood. Cultural change matters too. Behaviour, norms, and expectations influence consumption, mobility, and demand. Shifts in diet, travel, fashion, and housing affect emissions. These changes don't require perfection from individuals, but participation across society. Collective shifts, supported by infrastructure and policy, make sustainable choices easier and more accessible. Hope doesn't mean assuming everything will turn out fine. It means finding meaning and agency in the face of difficulty. Late hope is not naive. It acknowledges damage and risk, but refuses to give up on possibility. That hope is built in action. Not just large-scale innovation, but local efforts. Community gardens, neighbourhood cooling plans, youth climate groups, teachers reworking curricula, planners revising zoning laws, engineers redesigning grids. Mitigation and adaptation are not separate from justice. The people least responsible for emissions often face the harshest effects. Climate justice asks who benefits, who pays, and who decides. It pushes for inclusion, fairness, and accountability. A just transition means not just cleaner systems, but better ones, with more access, more dignity, and more resilience. Some change is inevitable, but much is still open. The difference between 1.5 and 2 degrees of warming is not academic. It affects crop yields, storm intensity, species survival, and human health. Every tenth of a degree matters. Every choice moves the needle. Whenever the idea of Earth becoming uninhabitable comes up, it doesn't take long before the conversation shifts to space. If this planet becomes too hot, too dry, too toxic, too stormy, could we simply move? Could humanity pack up, leave, and start fresh on a new world? It's a compelling idea. Science fiction has explored it for decades. Stories about interstellar travel, terraforming, space colonies, and new beginnings are common. They reflect both curiosity and a quiet fear that we might need an exit strategy. But turning that idea from fiction into reality involves a long list of questions: physical, technical, ethical, and logistical. The most frequently mentioned candidate is Mars. It's relatively close by planetary standards, and it's the most Earth-like in the solar system in terms of day length and the presence of land we could stand on. But Earth-like is generous. Mars has no breathable atmosphere. Its air is mostly carbon dioxide. Surface pressure is less than 1% of Earth's, meaning any human stepping outside without a pressurized suit would lose consciousness within minutes. Temperatures vary, but the average is about -60 degrees Celsius. Liquid water is rare and likely briny or buried deep underground. Radiation is another issue. Mars lacks a magnetic field like Earth's, so the surface is bombarded with cosmic rays and solar particles. On Earth, our atmosphere and magnetic field deflect or absorb most of this. On Mars, exposure would accumulate quickly, increasing cancer risk and degrading electronics. Any human outpost would need shielding, either underground, behind thick walls, or under artificial magnetic protection. Even if those hurdles were solved, there's the matter of self-sufficiency. A colony would need air, water, food, energy, and spare parts. Everything either has to be sent from Earth or produced on site. Growing food on Mars means finding ways to enrich the soil, add nutrients, manage light, and recycle water. Closed-loop life support systems, where every input and output is controlled, are still experimental. No one has built one that runs indefinitely. Even space stations require regular resupply. The journey itself is another constraint. Right now, it takes about 6 to 9 months to reach Mars using current propulsion. That means long exposure to microgravity, radiation, and isolation. Emergency help is not an option. The psychological and medical risks of such missions are being studied, but remain challenging. Some companies and agencies are optimistic. NASA, ESA, SpaceX, and others have sketched out visions of Mars missions in the coming decades. These missions would likely begin with robots and small crews, gradually scaling up, but scaling up is slow. A permanent, self-sustaining human population on Mars, capable of surviving without support from Earth, is not on the near horizon. Not impossible, but distant. Beyond Mars, options thin out. Venus is closer, but far more hostile, with surface temperatures hot enough to melt lead and pressures that would crush most vehicles. Its atmosphere is thick with carbon dioxide and sulfuric acid. The idea of floating cities in the upper atmosphere has been proposed where conditions are less extreme, but that's still speculative. The moons of Jupiter and Saturn, like Europa, Titan and Enceladus, are fascinating for science. They may even harbour microbial life, but they are cold, distant and difficult to reach. Their environments are not remotely habitable without heavy infrastructure. Any outposts there would be research stations, not homes. Then there's the idea of leaving the solar system entirely. Looking for exoplanets, worlds orbiting other stars, has become a major field in astronomy. Thousands have been discovered, some in the so-called habitable zone, where temperatures might allow liquid water. But even the closest of these is light years away. The technology to send humans, or even fast probes, to such distances doesn't yet exist. The physics of long-distance space travel, time, energy, protection, remain limiting. Terraforming is another concept that often enters the conversation. The idea is to take a hostile planet and make it more like Earth, warming Mars, thickening its atmosphere, releasing water, and eventually seeding it with plants. But the energy and timescales involved are massive. Terraforming would require planetary engineering on a scale far beyond anything humanity has done. Even optimistic models suggest it would take centuries, perhaps millennia, and may not even be possible with current physics and available materials. There's also the issue of ethics. If we find life elsewhere, microbial or otherwise, do we have the right to alter that world? Could we unintentionally destroy ecosystems we barely understand? The conversation about space colonization often focuses on technical feasibility, but the moral and ecological questions are just as complex. Even if humans did settle elsewhere, that wouldn't solve the problems on Earth. The vast majority of the population would remain here. Space migration, if it ever happens, will be limited, expensive, and slow. Earth will still be home to billions, and if the systems that support life here break down, agriculture, water, air, climate, the impact will be immediate. Space is not an escape hatch. It's a distant, difficult expansion. That doesn't mean space has no role. Satellites already support Earth systems, monitoring weather, tracking emissions, managing disasters, and providing communication. Space-based solar power, asteroid mining, or orbital manufacturing could help shift industries off-world over time. Telescopes, probes, and rovers expand our understanding of planetary systems, including our own. Exploring space is valuable, but saving Earth is essential. It's also worth noting that Earth is already incredibly well designed for life. Not by intention, but by billions of years of co-evolution. The atmosphere, magnetic field, biodiversity, oceans, weather, and soil all work together in a system that remains unmatched anywhere else we've seen. Even the most ambitious space habitats would struggle to replicate what Earth does naturally and continuously. Efforts to imagine life elsewhere, whether on Mars or in orbit, often use Earth-based analogues for practice. Research stations in Antarctica, underwater habitats, desert simulations, and the International Space Station all provide clues. These environments teach us about isolation, resource limits, and closed systems. But they also show how dependent we remain on external support, on resupply, connection, and redundancy. The dream of a second home is not misguided. It inspires exploration, innovation, and reflection. But it's not a replacement. No planet discovered so far, not one, matches Earth's combination of habitability, accessibility, and history. Even with all its problems, Earth is still the most livable place we know. Rather than imagining a clean slate elsewhere, some are turning attention to how Earth itself might be repaired. That includes ecological restoration, rewilding, replanting, restoring watersheds. It includes shifting economies to value sustainability and resilience. It includes recognizing that this planet, flawed and pressured as it is, still has more potential than any other. So the answer to the question, can we leave, is yes, eventually perhaps with limits. But the better question may be, should we treat this place as disposable or irreplaceable? When people ask if Earth might become uninhabitable, what they usually mean is whether it might become uninhabitable for us, for humans. But the planet doesn't require our presence to continue. It doesn't need buildings, electricity, language, or culture. If humanity were to disappear, gradually or suddenly, Earth would keep spinning. The sun would rise, rain would fall, tides would come and go. What would change is the way the world is organised, maintained, and interpreted. And over time, that absence would be felt. The idea of a world without people has been explored before. Books, documentaries, and simulations have mapped out what would happen if cities were abandoned, infrastructure left to decay, and ecosystems allowed to take over. The timelines vary, but some patterns are consistent. Within days, lights would go out. Power grids, left unmanaged, would fail as fuel runs out, or solar systems fall into disrepair. Water treatment plants would stop, and plumbing systems would back up. Buildings would start to deteriorate, slowly at first, then faster as weather, plants, and animals find their way back in. Within a few years, plants would grow unchecked in parks, sidewalks, and even high-rises. Vines would climb, roots would crack foundations, and grasses would spread. In warmer regions, insects and small animals would reclaim space quickly. Without traffic and noise, larger mammals might venture into once busy areas. Deer, coyotes, bears, and wild dogs would find new routes. In places where apex predators still exist, wolves, big cats, large birds, territories would shift. Domestic animals would struggle. Some might survive and adapt. Others, especially breeds highly dependent on human care, would decline. Pets left inside buildings would not last long. Farm animals might roam if fences fall, but many would face predation or starvation. Species that thrive in urban waste, rats, pigeons, raccoons, might flourish at first, then level off as food sources dwindle. In the oceans, shipping traffic would vanish. Underwater noise would drop. Fish populations might rebound in some areas, depending on pollution and habitat. Coral reefs stressed by warming could still bleach and collapse, but without additional pressures from trawling or tourism, recovery might be possible in cooler regions. Coastal cities would flood over time, especially those at or near sea level. Subways would fill with water. Roads would crack under plant roots and frost. Over decades, buildings would begin to collapse. Steel rusts, concrete crumbles, and glass fractures. Forests would spread into suburbs. Farmland would revert to scrub, then to young forest if the climate still supports it. Species that had been pushed to the margins might return. Others might disappear, depending on how much damage had already been done to their habitats. Nuclear facilities, without human oversight, pose risks. Many are designed with multiple layers of containment, but without cooling, spent fuel rods can overheat. In worst-case scenarios, some may leak radiation over time, but on a global scale, these would be localized events. Nature has shown it can persist in radiation zones, as in Chernobyl, though with complex and often harmful changes to ecosystems. Climate change wouldn't stop immediately. The carbon already released into the atmosphere would continue to affect temperature, weather, and sea levels for centuries, but without further emissions, the system would eventually begin to stabilize. Forests and oceans would slowly absorb carbon. Ice sheets, depending on how far they had melted, might continue retreating for a while, then potentially begin to grow again in some future cooler period. Plastic and synthetic chemicals would remain. Some break down under UV light or microbial action. Others persist for centuries or longer. Microplastics, already in oceans and soils, would continue to circulate. Over time, sediment layers would bury some of this material, creating geological markers of a human era. Satellites and space debris would orbit for decades or centuries. Some would fall back to Earth and burn up. Others would remain aloft, silent, reflecting sunlight occasionally. Probes on the Moon, Mars and beyond would sit untouched, exposed to cosmic radiation and dust. The technological footprint of humanity would linger, not forever, but long enough to leave a signature. In geological time, even that fades. Mountains rise, continents drift, ice ages come and go. Eventually cities become ruins, ruins become rubble, rubble becomes sediment. If life continues, it adapts. If it doesn't, the planet remains, shaped by weather and rock. Earth has survived impacts, extinctions, and extremes before. It could again, with or without intelligent observers. But intelligence, once it appears, changes things. It builds language, culture, tools, and memory. It reshapes environments, stores knowledge, and asks questions. If humans disappear, what happens to those things? Some would be lost quickly. Digital files, cloud storage, paper books exposed to the elements. Others might last longer. Stone carvings, metal artifacts, deep buried archives. But over time, most of it erodes. Without someone to interpret it, the meaning dissolves. There's a quiet irony in that. The species most capable of documenting its own story might still be forgotten. Unless another intelligence arises, either evolved or arriving from elsewhere, there would be no one to read, translate, or understand what came before. Earth would return to a more silent mode of history, recorded not in books, but in layers of soil, ice, and rock. Imagining this isn't necessarily an exercise in gloom. It's a perspective check. It reminds us that the planet is not fragile in the cosmic sense. What's fragile is the specific balance that supports life as we know it, especially complex, interdependent systems like forests, reefs, cities, and communities. What's at risk is not the planet, but the version of it that includes us and the things we care about. The absence of humans doesn't mean nothing matters. It means we're not the default. We're part of the system, but not required for it to function. That understanding can be grounding. It removes the idea that saving Earth is about saving abstract nature. It's about maintaining the conditions that allow complex life to persist, and that includes us. Earth doesn't pause. It rotates once every 24 hours, orbits the Sun once each year, tilts slightly on its axis, and wobbles over long cycles. These motions continue, whether we're watching or not, whether we build cities or let them fall, whether we speak about climate or choose silence. The world keeps moving, not untouched by what we do, but not centered on us either. That motion is oddly reassuring. Through all the change, stress, and uncertainty, the fundamentals continue. Sunlight warms the surface, gravity holds oceans in place, water evaporates, condenses, and returns. The seasons shift, plants grow, animals migrate. Even when systems are strained, many still function. That baseline, the rhythms that outlast any single storm or season, holds the space in which life can continue. Fragility doesn't mean weakness. A glass instrument can produce sound more precise than a metal one. A spiderweb, delicate though it looks, can absorb pressure and flex in the wind. Earth's systems are the same. They're strong in motion, in feedback, in balance. But that balance is made of components that can shift if pushed too hard or too quickly. For a long time we treated the planet like a background. Air was just air. Soil was dirt, oceans were scenery. But each is a system. Each responds to inputs and changes over time. We've learned, sometimes slowly, that extracting without limits or dumping without care changes the very conditions we rely on. And yet, despite centuries of pressure, most of the planet still works. Crops still grow, rivers still run, forests still breathe. That functionality, though imperfect, is something worth paying attention to. There's a tendency to think of Earth as either doomed or saved, to frame everything as a final choice, a single turning point. But systems don't change that way. Most environmental change is incremental, made of many small actions and decisions. Each one adds up. A few degrees warmer, a little more acid in the ocean, a species disappearing quietly, a flood that's not quite normal, then another. These aren't always dramatic. Often they feel like background noise, but over time they shape the future. That's also where action happens, in slow shifts, in planning codes, soil practices, transit upgrades, school lessons, tree plantings. It doesn't always look like rescue or revolution. It looks like care, maintenance, and patience. Like infrastructure that lasts longer, like energy that doesn't poison the air, like ecosystems that still function after storms. These things don't prevent all change. But they reduce the pressure. They buy time. They let systems breathe. We often expect change to feel bold or transformative. Sometimes it is, but often it's subtle. A slow transition in energy grids, a shift in diet that changes land use, a new law that protects a forest. These things add up, even if no one notices them immediately. Some of the most important work happens in quiet, in policy drafts, field measurements, back-office spreadsheets, school programs. Not glamorous, but essential. The strange comfort of a fragile world is that it still responds. It's not too late. That phrase has been repeated often, maybe too often, but its meaning is simple. We still live in a system where input affects output, where emissions today influence temperature decades from now, where choices now, what we build, protect, consume, teach, ripple outward. There's no point at which the world becomes completely lost. There are points where certain outcomes become locked in, or certain systems cross thresholds. But the idea of a fixed deadline misunderstands how dynamic systems behave. Climate change doesn't end with a single event. It unfolds, it accelerates or slows. It's shaped by what we do. That reality is both daunting and freeing. There's no single solution, no silver bullet, no button to press. But there are thousands of levers. Every country, sector, city, and household plays a part. The work is uneven, often unjust, and occasionally ineffective, but it's happening. More is known than ever before. Tools exist, networks grow, progress is possible, even if it's slower than we'd like, and Earth, despite all stress, still offers a baseline to work from. Soil still holds seeds, air still carries rain, coral still spawns, even in weakened reefs. These signs aren't reasons for complacency. They're reasons to act while systems still function, to protect what remains instead of waiting until it's gone. In that effort, the idea of permanence softens. Instead of seeking to fix the planet once and for all, the focus turns to ongoing care. Ecosystems need attention, not just preservation. Infrastructure needs updates, not just maintenance. Cultures evolve, technologies shift, values adapt. The world we build in the next few decades won't be the same as the one before, but it can still be livable. It can still support meaning, connection, and life. This isn't about returning to some perfect past or escaping into a better future. It's about meeting the present fully, understanding the systems that shape us, and shaping them in return. That includes science, but also culture, technology, but also empathy, planning, but also memory. The Earth continues whether we watch or not, but watching changes how we act. Knowing the atmosphere's chemistry shifts how we burn fuel. Knowing the ocean warms shifts how we fish. Knowing forests store carbon shifts how we build. Awareness isn't always enough, but it's the first step toward responsibility. So the planet spins, not untouched, not unchanging, but not broken beyond recognition. Not yet. That's where we are now, in a moment between paths, with tools in hand and time still on the clock. Not all the time we want, not as much as we had, but time enough to matter, time enough still to shape what comes next. Thank you for staying with this journey across centuries, systems, coastlines, and questions. Whether you listened to it all in one quiet stretch, or drifted in and out as the hours passed, the ideas are still here, moving gently through time with you. None of this was meant to alarm, only to observe, to notice what holds, what shifts, what still spins beneath our feet. The Earth is not asking for anything, but it's offering something. A pattern, a rhythm, a chance to keep going with a little more care. So wherever you are, in a city, a village, or somewhere in between, may you rest easy knowing the sky is still above you, the ground still beneath you, and the story still unfolding. Sleep well. The world will be here when you wake.